Good evening, class. Today is going to be our 20 lectures, and last time Ajahn added 3 more extra example to our video clips number 19. Okay. Today we're going to work on the last problem for the consistent deformation method for the beam. And before I go further, I would like to introduce you more problem. This one is the problem that Ajahn have added to the video clips of our 16 lecture. This is going to be the problem number 1 for that extra examples. And also this is the second one. And if you compare between this problem and the previous one, you may see the format of the problem can be, classified into 2 types. One, this one gonna based on the simple beam, and this one is going to be based on the cantilever beam. That's going to be our scope of study. And also in the third midterm examination this coming Sunday, the problem about the beam gonna be based on 2 types. One gonna be based on simple beam, another one can be cantilever beam and overhanging beam. And also I have added the third problem, and this one is going to be our third problem, and there are solutions in the video clips. Is the assignment for all you guys to go to the video clip and do the self-study. And we also have more problems such as this one. You may go to my previous year's video clips, okay, to study about it. By the meantime, we don't have much time. We have very limited time. Let me move to the problem that I'm planning to lecture you. Which one? It's going to be this one. What the difference between these 2 problems? I should say the problem over here, the beam subjected to only the distributed load. But the problem over here, the beam not only subjected to distributed load, but it's also subjected to the differential settlement at point B. So the second problem gonna be a bit formal. I'm gonna start by this one, and the author I left for you guys to study by yourself. Okay. Now, coming to this problem, we're going to solve it based on the method of consistent deformation, or some people may just call it the consistent deformation method. We're going to determine what? We're going to mean the reactions of the beams. Okay, that's going to be lower here, and in here. And again, we use the consistent deformation method. So based on this one, you got to consider this beam. It's going to have the reaction C sub Y, C sub H, B sub Y, and A sub Y over here. We have the total of 4 unknowns reaction, and then the beam continuous from A, B, C. So you guys have, okay guys, sorry for the hiccup. Okay, again, let me review it. We have the beam subjected to the load of 24 kilonewton per meter. and have the settlement over here for 12 millimeter. The beam have the cross section with the moment of inertia of 80 10 power 6 millimeter power 4. The beam made with the steel modulus of elasticity gonna be 200 gigapascal. Okay, we going to determine the reaction of the beam. That's gonna be A sub y, B sub y, C sub y, C sub y, and C sub x. And basis upon this one, after you determine the reaction, you should be able to draw the shear diagram, elastic curve, and also moment diagram. And then since you have 4 unknown of the reaction, that's going to be larger than the number of equation. We have only only one free body diagram. Sorry for this one. I should take this one and take it out. Okay, I got. And then you got to select the redundant. And following the table we have over here, we got to select the redundant in order that the beam gonna be in the form of simple beam. So we select B sub y as the redundant force. When we select the y as the redundant force, we come to very important step. Okay, we got to what? We got to separate the beam into two cases. We separate the beam into two cases, and I should say basis on the principle of superposition. So what we need to do, we just thinking about superposition in the form of simple beam. This beam can be separated into two beams, and first is going to subjected to the uniform load of 24 kilonewton per meter. So this one still keep in the form of roller, and this is in the form of the pin, and then it's subjected to the load. And then another one is going to be the beam. Now the beam going to subjected to the B sub y. It's still roller here and in here, but you got to put B sub y over here. Then you got to draw the elastic curve. Okay, in order you guys can draw the compatibility condition, and then this one and this one is similar to each other. So under application of the force, the slope over here at point A, theta sub A, is going to be larger than the slope over here for theta sub B, and the deflection should be something similar to this one, and this one gonna be theta sub B. It is in symmetry, not in symmetry. And then the second one, the beam subjected to B sub y, and then the load is in symmetry for the simple beam. Now you have phi sub A and you have phi sub B. You will have phi sub A equal to phi sub B. But for this one, you have theta sub A larger than theta sub B. And the deformation of this beam is going to be something like this one on the left portion. It's going to be the same as the one in the right portion. Okay. Now, you guys have what? you guys have the deformation and just set the deformation on the support B over here. This is gonna be delta B. And as I mentioned before, the deformation over here, you cannot determine it directly. Okay, you got to set B sub y equal to 1.0. Okay, and then the the deflection at B, okay, will be F sub BB. If you know this one is F sub BB due to one unit load, then this is going to be F sub BB and then time B sub Y. Okay. And then the third step, you got to come to write the compatibility condition. The compatibility condition occur at the point of the redundant force at point B. The compatibility condition at B. Okay. Now we have the deflection over here downward for 12 millimeter. Okay. If you have the problem like this one, okay, like this one, even though the load just different, the deflection at point B for this problem gonna be zero, no differential settlement. So you may say downward is gonna be positive. You will get the 12 millimeter over here gonna be 0.012 meter. Then you have equal sign over here. It's gonna be equal to what? This one, delta B. And then you have what? Plus over here. So it's gonna be plus. However, this one is opposite direction. So it's gonna pass by minus F sub B. And then you have this one for B sub Y. Okay. Now you got to rearrange equation. You have this one to be 0.012. And then you just take this one to be okay, this one not like that. Let me take this one over here. Okay, plus F sub B and then B sub Y, and then it's gonna be equal to delta sub B. Okay, and then you got to rearrange it because you're looking for B sub Y. So you may rewrite this one equal to delta sub B minus 0.012 meter and then divided by F sub B. Now, your compatibility condition can be used to determine the redundant force. But you got to what? You got F sub BB. Next step number 4. Okay, you determine the force displacement relationship that's gonna be delta sub B and F sub B. Okay, this problem, it's gonna be kind Okay, but if you guys know about the beam, okay, that's subjected to the force at the middle, okay, you should be able to remember the deflection over here, okay, and if you can remember it, you don't need to do any computation. This is gonna be PL cubed over 48 EI, okay, and another one you should be remember uniformly distributed load. You have the deformation on the left equal to the deformation on the right, and the deflection maximum gonna be WL power 4 times 5 divided by 384 EI. Okay, if you can remember, do it. If not, you must do the computation. Okay, but for the delta B is okay. You just take the result from that. Okay, from the delta B, from this picture, L over 2. Okay, so basis upon this one, you may say from this equation can be used from 0 to L over 2. This is very nice one. So you got to put this one. The negative, you don't worry. This is already downward. It's already downward. You should know about it. Negative. And then it's gonna be W okay, the x measure from here to here is gonna be L over 2. And then we have this one and put it into 16 and L cubed divided by 8. How come is L cubed divided by 8? It's gonna be L over 2 cubed, okay? And then minus 24 L. And then L cubed, okay? And then you have all of this gonna be L cubed. This one L cubed. This one L cubed. Take this one out. You should get this one to be W divided by 384 EI. And then you have L cubed. Take the L cubed, it's going to be L power 4. And then inside this is going to be 20 what is going to be 20 what? This is going to be 25, okay, minus 24. Then it's going to be equal to W divided by 384 EI. Oh, I forgot. It's going to be divided by 8. This one divided by 4. And this one is 9. This is going to be plus 9. Okay. And that is going to be 12 and then 6 over here. 6 over here. And then what you get, put this one into the number 24. So you got delta sub B is gonna be 6 times the load over here of 24 times 24. And then L, the length gonna be 8. This one L power 4. And then times 8 power 4. And then divided by 384. And then EI. Anyone helping me to determine it? Do it gonna be 640 over EI? Please check for me. 640 over EI. Anyone? 8 power 4 times 24 times 6. It's not 640. There are something wrong. There are something wrong. I got to change the problem if that's the case. Let me change. If I change L to 4 meter, what did you get? Change this one to 2 and change this one to 2. Huh? 96? How come? 24. Yes. Which one? At the deflection. You go back to the equation over there, right? You got 5. 2 minus, and then we go to our it again. Something must be wrong over here. Let me take this one. This one is equal to L over 2. You measure from here to here, and then that's going to be 16 L cubed over 2 cubed. Okay, and this is minus 24 L squared divided by 4, and then plus 9 L cubed. 3, this one, W okay, this is going to be something wrong over here. I find I take L cubed, and then this L times L cubed. This one L cubed. L cubed times L is L power 4. Okay, inside it is gonna be 16 divided by 8. Okay, and then it's gonna be 2. 16 divided by 8, gonna be 2. And this is gonna be 24 divided by 4 minus 6, and then two over here. This one must times it by 2. Okay, now we come over here. Over here, it's gonna be 5 times 24 times 8 power 4 divided by this is 2. Again, help me. What do you get? 640. Okay, that is right. Now I got this one downward. The second one, this picture, you don't have the result. So by using the conjugate beam method, the conjugate beams method, we looking for F sub BB. Now, our beam subjected to one symmetry. This is gonna be 0.5 and this also gonna be 0.5. Okay, you guys should be able to draw the shear diagram. This is gonna be minus 0.5 and then this is gonna be plus 0.5 and then process. Okay, and then x equal to minus 0.5. This is dv by dx equal to 0. S equal to 0. What's going to be the moment over here? Okay, moment over here minus this is point of 0 moment minus 0 equal to this area minus 0.5 times this is gonna be 4 meter. You got 0 over here and dm by dx equal to plus 0.5. Now you have the elastic curve you have the elastic weight for this one. The elastic weight gonna put in the downward direction like this one, and the beam gonna have this one for 2 over and this is gonna be b prime sub y and they are equal. Since they are equal, a sub y prime is gonna be the area here, 1/2 of what? This one 4 meter times 2 over EI. 2 cut 2. You have this one to be 4 over EI. Okay. Now you got to cut this one. Sub BB, you didn't mean the deflection F sub BB. That means F sub BB equivalent to M time. Okay, so basis upon this one, you have the beam in this portion of 4 meter and have this one to be 4 over EI. And then what you have is going to be the take the summation of the moment over here to be 0. You have what? You have M palm in this direction to be positive. M palm plus this one 1/2 of 4. And then this one is 2 over EI. And this is to be 4 over EI plus 4 over EI. The distance from here to here is going to be 4 over and then F sub BB, F sub BB is going to be equal to this one. Take 4 by 4 is going to be 16 over EI, and then minus 16 over 3EI. And if you take this one, 16 over EI is going to be 1 minus 1/3. This is going to be 2/3. And then you choose this one to be 10.67 over EI and upward. Okay, you got this one. Now you are ready. You got the fraction. So the first step, okay, the first step, you determine B sub y. Just take this one, B sub y equal to in the meter, you got to put it to be 640 and then divided by EI. Take this one up over here, and this is going to be 200 gigapascal. 210 minus 9 Newton per square meter. Change this one to be 210 power 6 kilonewton per square meter. Why? Because it's gonna be 80 10 minus 6 meter powerful. Okay, then if you put everything, you should get this one to be 0.040 meter, right? It's gonna be 0.040 meter. Now, this one, okay, you cannot compute it, okay? Divided by, if you follow the top over here, 200, and then this one for 80. You get this one for what? Okay, 0 point, very small. 0 point, okay, 0.06. How many zero? Zero, okay. 0, and then 6, and then 6, and then 7. Ready to compute? Note on this one. Due to the settlement, okay, due to the settlement, you got to compute the value. If there is no settlement, If this is 0, okay, you can cut EI by the EI. Computation gonna be easier. Okay, when we have settlement, it's gonna be a bit more complicated. Take this one for delta sub B, 0.040, and then minus 69. Okay, 69. Okay, follow Chang. Thank you very much, Chang. You are my win under wing under my wing. Okay, and then you should get this one to be 42 kilo Newton, and that is going to be positive. Since this is positive, this is going to be in the upward direction as our redundant force given over here. Now, this is going to be 42 kilonewton. We determine the reactions and then the shear force diagram and moment diagram and elastic curve. Now, coming into this one, let me take the area around here. And if you do the summation of f sub x equal to 0, for sure, c sub x gonna be 0. Now, let me take you to this one. It's up to what you convenient. If you take the summation moment about a equal to 0, you can see. Let me take about b is c. It's going to be more convenient. C, okay, take it about c. We have a sub y. 8 times a sub y. This is 4 meter. This is 4 meter. Resultant force over here rotate in the opposite direction. This is 24 times this one 4. This is 24 times 4. And the distance from here to here is going to be what? 6. Okay, 24 times 4 times 6. You should get a supply to be 51. Okay, a sub y should be 50. Sub y equal to 0. Now, you're looking for b sub y, and then plus 51. Okay, upward plus 51. And then this one plus c sub y equal to 24 times the distance of 4. So your b sub y is going to be 96. And then minus 51. And then minus 42. And then that's going to be 96 minus 93. This is not correct. This one 48, 48 and 48, 90 hertz. This is it's gonna be 3 kilonewton. Okay, and then it's gonna be in this upward direction. This is gonna be 3. Okay, we have everything. This is 3 kilonewton. We come to drawing the shear diagram X meter, and then this is gonna be in V kilonewton. Let me take you guys over here. We have this is for 0 meter. We take it from the left to the right. This is gonna be 4. This is gonna be 8. And then we have 51. Okay, if you take this one 51 by the scale of 50 kilonewton per 10 millimeter. So you may have this one for about 10 millimeter upward plus 51. And then you have this one, dV by dx equal to minus 24. What's gonna be the shear force at 4 meter? So we have V over here minus 51, and it's gonna be negative of this force, and this is gonna be 24 times 4. V is gonna be minus 96 and then plus 51. Okay, and then you got to have this one to be minus 45 kilonewton. By doing this one gonna be downward, and based on 45, and this one is gonna be 9 millimeter minus 45 minus 45, and then the line over here gonna have negative slope. So this is gonna be negative slope. We have this one for 0, and our slope gonna be the same for every point. Okay, mark it. Ajan know about it. If you very sure about it, just point it out. Now, 42 is upward. Take this one upward by 42. This one upward by 42. You have plus 42 minus 45. You're gonna have minus 3. This one gonna be minus 3. And no W here. W here is 0. So dV by dx gonna be 0. You're gonna have this constant to be minus 3 over here. And then you have upward 3 kilonewton forces. You have plus, minus, minus. Okay. Now, you have 0 over here. What's going to be the importance of this point? This is going to be maximum, minimum moment, and then 51 divided by this one, x, is going to be slope of 24. So x, take it up, going to be 51 divided by 24. And you should get this one to be 2.125. Yep, 2.125 meter. Now, let me move to moment diagram again. We have this one for the moment kilonewton meter and 0 for 8 x meter. No external moment here and here. Mark it 0, mark it 0. Then 51 over here. dm by dx is gonna be plus 51. Okay, it's gonna be upward 51. And what's gonna be the moment over here? Okay, and moment over here minus 0 over here, and then it's gonna be equal to the area here, 1/2 of 2.125, and then times 51. Okay, you should get this one to be 54.875. So M is going to be 54.185 kilonewton meter. If you set the scale 50 kilonewton meter per 10 millimeter, just put the scale here. This is a bit more like approximately 11. It's gonna be over here, okay? And what's gonna be slope here? What's gonna be slope here? You cannot compute it yet. It's gonna be minus 45. I forgot. Hey, this is one important thing. Ajahn put this one wrong. This is not correct. We have this one for dm by dx equal to 0. We got to determine the moment here first before we can determine this one. M minus 0. That's this one. Oh, not this one. This is going to be over here, the maximum. Not this point. Not this point. It's going to be this point. Moment at this point. At this point, not that point, at this point, minus 0. Okay, and it's going to be equal to this one. And this is going to be 54. Okay, and then the slope over here going to be 0. I should say the slope over here is 0. The value over here is going to be 54.185, and the curve must be something like this one. Okay. And then up until this one, what's going to be the moment here? Now, the moment here minus this one. 54.185 moment here minus here equal to this area. Okay, it's going to be 1/2 of this one, 4 minus 2.125, and this is going to be minus 45. And if you put it, what did you get? When to get M is going to be plus 54.185 and minus 22.5 times 1.875. Chang, did you get? Even 0.99. Let's put it to be 12. Even 0.9975. Okay, let's put it into 12.0 kilonewton meter. That's positive. Okay, that's positive. And then this one supposed to be somewhere over here. And value gonna be 12. And the slope over here gonna be negative of minus 45. The m by dx gonna be minus 45, and the curve is gonna be something about this one. Okay, and then the value of the moment, this is minus 3. So dm by dx gonna be minus 3, and since this one is 0, okay, you have moment like this one. And then you have what? All of these, they are positive. And then what's going to be your elastic curve? Now, draw your elastic curve. Let me draw it over here. We have the roller here, roller here, and pin here. And we have the settlement of 12 millimeter. So this is gonna be 12 millimeter. And then our structure, this one gonna be curved a lot. This one gonna curve a lot. Okay, due to the large moment. And then the small moment over here is gonna be nearly straight line. Just curve this one back. Okay, guys. Sorry for the inconvenience. The computer system just keep catching, and then we have much more problem on the analysis of statically indeterminate beam, and I should put this example for you guys in order to you have a chance to compare with the previous one. Again, in the final examination, Ajahn will provide you this kind of information. However, the point load is going to be really simple, right? You can use the conjugate beam to solve it easily. But for this one, when you see this one, just taking the image and then you can see we have 4 unknown. Again, that's going to be more than the number of equation of equilibrium. And then you're going to have the degree of indeterminacy to be 1. And then you should select the one corresponding to the information Ajahn given. That means you got to select B sub y as redundant. If you not select B sub y as the redundant, you cannot use this given information to determine the diffraction. Okay, so you're going to put it in the form of simple beam as the given diffraction table. Let me put it like this one. Okay, that's gonna help you. I mean, in the final examination. Then, following this one, you should be able to draw the beam. Now, that's gonna be 6, 6. It's gonna be like the beam like this one. That's gonna be 1, 2, and then 4. Okay, the beam can be roller over here, roller over here, and then you put the pin over here. Now you just change the roller. The beam over here will be modified into this one. Since you take this one as your redundant, so the beam subjected 10 kilonewton over here and also 2 kilonewton over here, and that's gonna subject them to this is gonna be B sub y. And as you may know, you got to separate the beam into two pictures basis on the principle again of superposition. You put this one into in the form of simple beam, separate the beam into two pictures, and then one is gonna subject that to the given loading, and for the beam subjected to given loading, most of the time we call this one primary beams. I forgot to tell you from the previous problem. And the second one, the beam gonna subject that to B sub y. Again, this is gonna be roller. This is gonna be roller, and this is gonna be the pin. The beam gonna have the deflection, okay, and then the first one gonna be over here, downward, okay, and we interested at this point B. So this is gonna be delta B, and for this one, you have this kind of direction like this one, and I should say the elastic curve on the left and on the right, they must be the same. And for this picture, B sub y is unknown. So you got to set B sub y equal to 0. The deflection at point B, okay, due to the load, 1.0 at B is F sub BB. You got to set this one in order to provide the information over here. It's gonna be F sub BB B sub Y. Okay, and then you can use the information given in this two picture to determine the deflection here. And also you can use this one to compute the deflection here. And then the last one you got to mention about the compatibility. The compatibility condition. That's going to be a bit more complicated. At what? At B. You got to say this is occur at B is what? This is 0. And then that one is positive plus equal to plus this delta sub B opposite direction minus F sub B sub Y. So B sub Y gonna be delta sub B divided by F sub B, and then the problem come to chapter 7 to determine the deflection. And now I asking you to use the knowledge from mechanics of material and use it over here. Okay? Any question? Then after you get B sub Y, you can compute for A sub Y, C sub Y. For this one, summation F sub X equal to 0, C sub X is 0 automatically, correct? Okay. Again, let me repeat it. We have the form of problem in the form of simple beam, and we have the form of problem in the form of cantilever beam. And most of the time, Ajahn also provide you with the deflection table. So any question? Okay, no question. Let me finish the first problem on our final examination over here. And let me move to the flip. Okay, the second problem. Okay. And the detail of this problem you can see from our previous video clips. Okay. Now, for the frame, let me take you to the PowerPoint, and then again, frame is going to be our second learning objective and going to be our second problem in our final examination. And there are a number of frames. You can determine the what's so-called degree of indeterminacy by finding the unknown reaction. For this one, you can see the reaction from this beam may put up at this point, may put up at this point, and also also the frame may have their dead load. Okay, the frame may have the dead load. The dead load may put it over the beam over here, And then in some cases, the frame also subjected to the wind load. So the wind load may come in this size of the structure. All of these are external loading. Then you got to take a close look at the support of the structure. If this is going to be thin, okay, you may just put it in a small foundation and no pipe, okay, and then small for small foundation and then plus no pipe, okay, and then you may need help it as the you have how many? You have 4 unknown. Okay, this is going to have you for A sub X, and then this one for A sub Y, this one for, let's see, A, B, C, D sub X, and this one for D sub Y. You have 4. And since the connection of the frame in this one is a kind of rigid joint, okay, the free body diagram of this one gonna be n equal to 1, and each free body diagram have 3 equations. So the equation gonna be 3. So 4 minus 3, you have DOI equal to 1. You got to select, okay, what? You got to select one redundant force. And again, I will focus on this one. But if you say you have a big foundation and also use the pie, now the frame can modeling to have fixed support. When you have fixed support, what happens? You have 1, 2, 3 reaction, and then 4, 5, and 6 reaction, and then all the connection rigid joint. You have 3 times n equal to 1. So this problem gonna have DOI equal to 3. This one gonna be very tough if you use the force method. We will consider this kind of frame in the structural analysis next term. We will talking about the structural analysis. We have the method to compute the structure having high degree of indeterminacy, such as the slope diffraction method. Okay, and what we have another one is going to be moment distribution. We will talking about it later, but I'm provide this opportunity to tell you more degree of indeterminacy gonna come, but we have more method to tackle it. Now let me move to this one. Did you have a chance to visit the site? Okay, take a look at it. Okay, enjoy your discussion with an ice cream, and then you can model again. This one gonna be pin. Okay, the structure subjected to sometimes they call it vertical load. Okay, and many times they call it gravitational loads. Okay, and also most of gravitational load gonna be the dead load and also the structure subjected to the wind. Okay, and that's called horizontal load, and many times it's called lateral load. All of these terminal terms as international CE student, you got to recognize them. Okay, and then again, following this one, the structure will have 1 degree of indeterminacy. Now, this coming afternoon, you guys supposed to have a lab, okay? Yesterday, you have a chance to meet the frame also, right? This frame have fixed support. If you go over there, you can see there is the steel plate fixed by mini bolt and also have stiffener. Okay, again, this frame you may consider it as the individual frame, and as the individual frame is going to have DOI equal to what? In this, let me put it in yellow. Okay, in this direction, in this direction, in this direction. No, since it's pin, right? It's gonna have DOI equal to 3. Okay, if this is pin is only 1, it's gonna be 3. If this is fixed connection, and then there is another direction when you design the frame, you got to consider this one also. This frame will connect from this one to this one. And now this frame, the green one, gonna be more complicated based on 3, 3, 3, 3. I should ask you what gonna be the DOI of this green frame. Anyone hear me? That's gonna be 3, 3, 3, 3. You're gonna have 12. Okay, the 12, right? And you have all connected. You have 3 equations. This is gonna be DOI equal to 9. Okay, you can check it based on our previous discussion. You just take this one, cut 3, 3, 3. If you cut it like this, you have 9 degree of indeterminacy also. Okay, which method provide the same result. We weren't interested in the frame with very high degree of freedom. In this discussion, only 1 degree of freedom is going to be our main focus. And then based upon that, what's going to be the frame with 1 degree of indeterminacy? This is the one of the problem. Is have the pin support, okay? Pin support. So this one gonna have DOI equal to 4. Equation of equilibrium 3 is gonna be 1. What the other thing else? You may have this one fixed, okay? And then we have this frame with the roller. This one also have 1 degree of indeterminacy. And if you have again frame with this one, 3 member, and this one is pin, and this one is pin. This also 1 degree of indeterminacy. And if this one is fixed, and this one gonna be the roller, all of the frame gonna have DOI equal to 1. Okay, even though you have a frame with this kind of form. Okay, we have this one, and then you have this one to be fixed and this one to be the roller. This also have 1 degree of indeterminacy. So the format of the frame gonna be various. Okay, we have variety of the format of the structure, but the concept gonna be the same. You got to first select the redundant. Now, when we talking about the analysis of this frame, you select the redundant. Okay, when you select the redundant, the problem is you got to what? Again, using the consistent deformation, you got to determine the compatibility condition. Concept gonna be the same. How to get the compatibility condition? You use the principle of superposition, separate the frame into two more frames. And then you got to determine what? To determine the deformation of each frame. Okay, consider their elastic curve and put it into the compatibility condition. Now, you got to determine the deformation of each cases. Again, chapter 7 comes. Okay, chapter 7 comes. So you got to be very careful on the study of chapter 7 on this Sunday. You got to do your best because it's going to be used next in chapter 8. Okay, then after you can determine the redundant, later you determine the reaction. Okay, the author reaction. After determine the reaction, you can draw the shear force diagram. You can draw the bending moment diagram, and you may draw the elastic curve also. Even the beam have equal EI. That means this one has EI, this one has EI. Many times, Ajahn didn't provide that. Ajahn may say, hey, this has 2 EI, this one has EI. Beware about it. Okay, it's very important to be very careful on the problem statement. E is going to be 200 gigapascal. That means this is going to be the steel frame, and moment of inertia going to be 250 10 power 6, since it have 1 degree of indeterminacy. Let's take C sub y as the redundant. When you take C sub y as the redundant, the support over there must change from the pin to be the roller. Now, C sub y going to be the redundant, right? This keep the same pin, but this one changes to be the roller. By using the principle of superposition, the frame will have pin and roller. So this one equivalent to the frame, pin and roller, plus pin and roller. By this one must subjected to the force C sub x equal to 1. Then if this is C sub x, if this is C sub x, the deformation over here gonna be the deformation at point C due to the application of 1 point unit force at point C. There are 2 C. The first one at point C. The second one due to the 1 unit load at point C. Okay, and then it's gonna have by C sub x to get the equivalent deformation. Then this is going to be 2 problems. After you separate into 2 cases, and then you draft or you sketch the elastic curve. When you sketch the elastic curve of the frame, you can draw the compatibility condition again at point C in horizontal direction. Actually, you got to put the word horizontal direction. The horizontal direction deformation over here gonna be what? Gonna be 0, equal to this one move from the left to the right, and then it's gonna be 0 plus. Okay, this is move toward the left to the right, and then plus this one also move from the left to the right. Now, the problem change to determining the displacement delta sub c in the horizontal and f sub cc using the unit load method, or you may say using the method of virtual work again. Review it. Okay, you have a chance. This is going to be external virtual work. This is going to be external virtual work. Going to be equal to the internal virtual work. And then what you do is you got to assume 1.0 unit load applied in the same direction as the delta sub ch. Assume it, okay, 1 unit load, okay, apply to that one. So assume this 1 unit load. Then assume force times the real displacement. We call it external virtual work. Then this small 1.0 unit load produce small bending moment equation F. Okay, and the loading provide the capital moment M. Okay, and you know capital moment M divided by the EI and time d theta. This is the real change of slope at a given point. Okay, and then for the work due to the moment, you got to time the moment. You got to time the moment by the change in the slope. Okay, so another step, you got to determine capital M. Okay, now the problem comes to determining the capital M. Again, very important is going to be set the coordinate. The coordinate is very important both for capital M and small m moment. It's going to be the same. Okay, remember another thing going to be the same. Another thing, let me say, you got to do another one. You got to set the sign convention. The sign convention for what? For capital M and small m. They're going to be the same two things. Okay, let's put this one. Okay, to determine the reaction. Ajahn won't do it. You can do by yourself. Set this one to be x1. Set this one to be x2. Okay. Ajahn, may I use the other thing, such as this one to be x1, this one to be x2. It's up to you. But it's going to be very tough, believe me. Okay. Why I select the red coordinate? Because it's easier than the light blue coordinate. Okay. Now, you cut this one to be x1. Let me erase of this one. And then set this one to be for x1. And then you can take the moment over here. Okay. Draw the free body diagram. This one provide no moment. Summation of the moment equal to 0. For this one, capital M1 rotate in this direction positive. And this is going to be the resultant force plus 2. This is 2. Times what? This is x1. And then the distance from here to here gonna be x1 divided by 2. They rotate in the same direction, but we have 12 kilonewton in the opposite direction. So your M1 is going to be equal to 12 x1 table x1 minus cut x1 square. That's going to be your first one of the capital M1. Okay. And then do the same thing for the second portion. Take the moment over here. Oh, my point wrong on this one. Do the correction also. Summation of the moment equal to zero. This is going to be M2. Rotate in the same direction. M2 equal to, very simple, 6 times x2. And that's it. Okay. And the coordinate and the sign of the moment going to be used here. Okay, due to the 1 unit load, you can determine the reaction. Use the same coordinate. Okay, and then cut it over here. Summation of the moment equal to 0. This is small m1 and gonna be equal to x1. Okay, and then you get this one. And then for this one, cut it over here. This is summation equal to 0, m2. The same sign. See, the same sign. Going to be, this is x2. You get x m small m1 equal to x1, small m2 equal to x2. Put it into your calculator. Do the integration. Now, you guys are good at it already, right? Use your calculator to do the integration. If not, you still have another 3 more days to do so. Okay. If you don't do so, you still need to do so next time in the final examination. Okay. You get the result. Now, for the next one, you got to determine the reaction for what? Sorry, the deformation for the 1.0 unit load. And you can note that, hey, this F sub CC, when we determine it, is going to be the same picture as this one. The same. Okay? If you note it, and then use the same result and do the integration. Okay? And then you plug this one into the compatibility condition, and this is plus, this is plus. You get C sub x to be negative. Hey, how come, Ajahn, it's going to be negative? Because the redundant force that you use is not correct. Okay, the direction of it gonna be in the opposite direction. You have this one to be your correct direction of the redundant. Now, use your knowledge from engineering statics from chapter 4 of this chapter. Determine the reaction and then draw the shear diagram, draw the moment diagram, and draw the elastic curve. All the detail of this one, Ajahn will come back later. Okay. Now, let me move to another format. Okay. Previous one, you have the frame with the pin. Okay. You have the frame with the pin. Now, very important format is going to be fixed and also roller over here. That's going to be what? For unknown. We have 3 equations. So our DOI going to be equal to 1. So basis upon this one, which one you going to select for your redundant? It can be C sub y. It can be C sub x. It also can be M sub C. And it can be A sub y. The principle is select the easiest. Okay. In this one, you can see if you take A sub y as the redundant, your structure will change to this form of frame. and it's going to be the easiest one to determine the deformation. Now come to a sub y as the redundant, and we have the reason behind it. Okay, for the beam, select it basis upon deflection table. Okay, for the frame, select it basis on the easiest to determine the deflection. Now, you separate the beam into two cases. Okay, one, this called primary frame. Primary frame is the simple frame. After you select the redundant, you get statically determinate frame. Okay, and then subjected to external force, and then plus the same frame subjected to the redundant, and then you got to again draft your elastic curve. Okay, or you say you sketch the elastic curve. When you sketch the elastic curve, just sketch for this one, you know it very well. Ajahn already lecture you why they put this portion in a straight line. You see, they put it in a straight line, and this portion is going to be curved. Why? Why? You noted on that, right? Why? Because this portion, if you cut it, the moment gonna be zero. Okay, and if you cut this portion again, the moment here gonna be zero. But if you cut it over here, the frame will subjected to 50 kilonewton, and then it's subjected to the moment. Okay, right? And then this is going to be capital M3 for sure. Capital M2 for the zero. Capital M1 going to be zero. And then for this one, is this one going to be correct? I don't think so. This one supposed to be something like this one. Okay. The textbook is not correct. Okay. Many times when you read the textbook, try to study about it. It should be in my green line. Okay, the elastic curve. And again, we have this one to be a sub y f sub a when a f sub a is the vertical deflection due to a sub y to be zero. Okay, now we come to compatibility condition of what? This one is zero. Okay, why? Because this one used to be the roller. Okay, even though you change a sub y, reaction prevent deflection. Okay, and then this is delta sub a downward, and you get the negative because f sub a upward. Now a sub y is the form like this one. Okay, Ajahn, that means you got to determine two deflection in the examination. Don't worry, Ajahn Siddhichai very kind. I will provide one topic for you. Okay, not all. One. Okay. Another one you got to use your knowledge. And see, that means you got to spend more time for this problem in the final examination more than you got to do it in the third midterm examination. Because on the third, you just determine the deflection. This one, you got to draw the last term. You got to draw the moment diagram, shear diagram, determine the reaction. Now, we got to determine the displacement. And I said, the displacement equation is called load displacement relationship in the big pictures. Okay, in the general terms. Take this one. Okay, take this one. Cut it as Ajahn told you. Two things. Use the same sign convention. Use the same coordinate system. This is gonna be x1. Okay, and then you got to use this one for the capital M1. and then take this one. Again, this is 0. Ajahn already told you about this. Then cut it over here. Draw it another free body diagram. Put this one as the x2 and use this one, use this one, use this one, use this one. Ajahn reverse the direction of the textbook. Okay, this is gonna be capital M2 gonna be 0, and the last one cut it over here. The frame gonna be subjected to 50, and this is gonna be your x3, and you use this one to be capital M3. Okay, capital M3 rotate in the opposite direction of this one is gonna be 50x3. Okay, 50x3, and the same gonna be this one for the beam that's subjected to 1 unit load. Okay, we check A sub y to be 1.0 unit load. And then you guys should be able to again what the first portion use the same this x1 and due to the load over here, this is gonna be small m. Take the moment over here, that's gonna be equal to x1. Okay, you got to have this one for x1 for the pink, and for this one do the same thing, cut it and use the same sign convention. This one, same sign convention, x2. Use the same sign of the moment. You have the force here, 1.04 meter. Take the moment over here. This is going to be your small m. Okay, small m. Why? Summation moment equal to 0. This is m2 plus 1 times 4 equal to 0. That's why you get negative 4. Okay, the same direction, the same thing. You cut it over here, and then this is going to be your x3, and this is just be small m3, small m3. This is going to be your force 1.0, and the distance from here to here is 4 meters. Your summation moment equal to 0 over here. M3 rotate in the same direction plus 1 times 4 equal to 0. So your M3 is going to be negative. Okay. And in short, for this one, this is 0 times this one is going to be 0. Okay. And then the second one, this is going to be M2, and then times this one is going to be 0, and the last one we have only M3. Okay, M3, capital M3 times small m3, you get the result to be negative. Okay, why it's going to be negative? You set this one upward. Okay, that means the real thing is gonna be the downward. Okay, as you may assume it. Then coming to the next one. Hey, Ajahn, this one is the same as this one, right? This one gonna be the same as this one. Okay, that means you got to be able to determine small m, do the integration, get the positive, because f sub AA is upward as you put 1 unit first. Okay, my PowerPoint have some time, so please correct it. And then you get the result. You get the reaction A sub y. Then go back to use the knowledge from chapter 4, draw the shear diagram, draw the elastic term. Okay, And then you got to do what? You got to be able to draw the elastic curve. Use what Ajahn teach you a lot from chapter 7 and draw the elastic curve. Okay, you will get the result something like this one. So, any question? No question. Coming to the third format. Okay. Okay, this one, let me skip it. Most of the time, I won't use the reaction of the moment to be the redundant form. You may study by yourself if you prefer. Okay. And the third one is going to be this one. This one. To be very quick. Okay, this one. Okay. This one, remember. Don't worry. Which one going to be your redundant? The reaction that's gonna change the structure to be a very simple one. I will put this cantilever, put this one, so I will select C sub y as the redundant because the structure on the form like this one going to be easy to analyze for the deflection. Okay, only C sub y. Since this have DOI equal to 1. And then do the same thing. Okay, separate the frame into two. One is going to be primary frame subjected to this one 12 kilonewton meter plus another one subjected to C sub y. Use your imagine and imagine for what? Imagine for the deflection. Actually, this is not correct. It's supposed to be something like this one. It's going to be correct. Okay, this is not correct. Let me do the correction. And again, this is going to be delta sub C. And this one also, the correction elastic curve should be something like this one. And then because this one is a rigid joint, and then you can draw this one. Oh, the problem have what? Settlement also is set at this point is have 4 millimeter settlement. Okay, then you got to rearrange this one, and this one going to be very close to Ajahn tell you. You got to move this. This one is going to be 0.004 plus delta sub C equal to C sub y F sub CC. C sub y F sub CC going to be delta C plus 0.004 divided by F sub CC. Determine both of the load displacement relationship. Okay, then you use the knowledge from method of virtual work. Separate this one, you got to determine what? You got to determine delta sub C. So for this frame, you use the x1 over here, and then use x2 over here, and use x3 over here. You're going to use the same coordinate. Okay, this one gonna be x3 for the load of 1 unit. That's gonna put it. Actually, you got to put 1.0 over here also. This is gonna be 1.0 to be complete, and this is 1.0 times the deflection external virtual work. And then for this M, okay, determine it by using the sign convention. And I should say, put the same sign, okay, coordinate first. Put the same coordinate first, and then put the same sign convention. Okay, and then you will get the result for delta sub C. Okay, again, F sub CC, Ajahn is going to be the same of this one and the same of this one. All right, yes, be the same. Okay, and don't worry, Ajahn only asks you to determine one of them. Okay, and then for sure you will get this one for C sub 1. And for the frame and for the beam with the settlement, a bit of more complicated calculation occur because you got to determine the exact value of the displacement before you can get the redundant force. But if there is no settlement, EI going to cut EI. The computation going to be easy. So C sub Y is here. You use this one to determine the reaction and then draw the elas, draw the shear diagram, draw the moment diagram, and then you get the elastic curve also. Next time, I will not go to the task yet. Next time, I will show you manual calculation. I only provide you the extra example for you to further study, and again, I should confirm the knowledge from chapter 7. Very important for chapter 8. Okay, any question for the lecture here? I will put 3 more extra example, and the total time gonna be like a 4 hour with eclipse. Okay, you can speed up 2 times. It's going to reduce the time to 2 hours. Okay. Thank you for your attention.
Okay, hello student. We're going to solve the statically indeterminate rigid frame as shown here. This frame has the fixed support at the C and has the lower support at the A. So if you check this, you may see we will have the reaction over here. Over here, this is going to be C sub X, and this is going to be C sub Y. And we also have the moment M sub C here. And for at point A, we have this as the A sub Y. And you may see we have 4 unknown. So our degree of indeterminacy gonna be like 4 minus 3 equation of equilibrium. So we have degree of indeterminacy of 1. And then we are going to solve this by using the consistent deformation. And this problem asks us to use the A sub Y to be redundant. Typically, when we select the point or the reaction to be the redundant, we usually to select the support that has only one, okay, redundant, or we select the support that has small amount of reaction. For this one, this has 3, this have 1, so we select, okay, the support, okay, with actually is with small amount of reaction. So we didn't select C sub X or C sub Y. That's going to be difficult to solve for the diffraction, okay. And this beam is what's so called the, no, it should not a steel frame. This one is supposed to be the steel reinforced concrete. Okay, this is the steel reinforced concrete. So it is going to be the RC frame. And what it has the modulus of elasticity of 20 gigapascal and the moment of inertia of 610 power 6. So if you like to see this is in the unit of kilonewton. So this is going to be 10 power 6 kilonewton per square meter. And since we use the square, we use the unit of meter here, this is going to be 610 minus 6 meter power 4. You may do the unit conversion like this. And then since we have the a sub y as the redundant as specified here, so the first one, that's we gonna start of this after we find as the a sub y, the a sub y, the a sub y, the a sub y is the redundant force. Okay, thus we can consider the frame. Okay, we can consider into two cases based on the principle of superposition. So we can separate the beam or consider this frame. We can the frame into two parts. So let's take this one, and if you can measure this is going to be about 3 centimeters. Then we have this one. So our frame gonna be like this one. This is 3 centimeters. We put this one for 3 centimeters. We separate the frame into two cases. So what are they? It's going to separate into two cases. The one will subjected to the applied force, okay, which we call it the primary frame. So this frame, when you set a sub y as the redundant force, so the statically indeterminate frame, indeterminate frame will change to statically determinate frame. Okay, determinate frame. So our frame will change into this, and what we have is the one we will call is primary frame. This one will be called the primary frame. The primary frame is the frame that's subjected to the applied forces. So it's subjected to 10 kilonewton, and also this one 2 kilonewton per meter. So it's important when you select the redundant force. Okay, your frame just change from statically indeterminate to statically determinate, and you use the principle of superposition, separate the beam into two cases. One is called the primary frame. Okay, this is subjected to the given loading, and another one is this one that's subjected to the redundant, the a sub y. Okay, this frame is subject to redundant, and then we have this one a, b, c, and a, b, c. Okay, we have separate into two cases, and this one is the frame subjected to the redundant force a sub y. Okay, and now we will set what so-called the compatibility condition. So second, okay, we will set for the compatibility condition, and since the a sub y as our redundant, so the compatibility condition at a, okay, we will this, and we can set the compatibility condition by what? Okay, by considering the deformation of the frame we have. Okay, the deformation of the frame, this frame is subjected to this force, and this is the roller, so it may be possible this one will move from A to A palm, and if this one move from A to A palm, this is going to be B palm. So our structure subjected to this uniform force. So it's maybe deformed like this. And since this is going to keep the right angle, so this one will deform corresponding to its support, fixed support here. So the zeta sub c is 0. Also, the delta sub c phi and delta sub c h, all of them are 0. So this is fixed. Okay, and what we have now is the deformation here. The delta A vertical is 0. At this point, there is no vertical because there is the redundant force of the A sub y. Anyway, over here, we will have the deformation delta A horizontal. Okay, and also this one is going to be delta B horizontal. Since the beam and the frames have the beam and the frames have very small axial deformation. Okay, and then you may get this one, delta sub BH will equals to delta sub AH. And also, since there is no shortening or axial deformation of the beam of the column BC, so the delta B phi equal to 0. Okay, and the last one, the rotation. Over here you will have zeta sub A, and respond to this, you're going to have the rotation, this one and this one of zeta sub B. So that's all the deformation of the frame. That's we know some and some we won't know. What we know is here, that is going to be the geometric boundary condition of the beam. But what we don't know, we can determine later if we like to. Okay, and what else? The primary frame. The primary frame is subjected to this kind of force, and I believe it's going to move like this. And since this is the rigid joist, so it's going to keep this one as the right angle, and this is fixed. So this is going to be the deformation of this beam, and you may say that since the A sub y as the redundant, so we're going to interest that in this. What is this? This is going to be the delta at what? At A in the vertical direction for this one. Okay, and also this one, this guy going to deform something like this. If you can imagine it, right? This is going to be the right angle, and what we consider is the deformation in this direction. Okay, that is going to be, we don't know A sub y, right? Actually, this one is not correct. It's supposed to be here to be a better one. So it's going to be at the point of A. Okay, this is the delta. Okay, this is more correct than before. And this one going to be what? This one going to be A sub y, don't know. So usually we will set A sub y equal to 1 to determine this. This is going to be F. F is the symbol of the deflection due to 1 unit load. And at what? At A. Due to the applied force at A. So this is F sub A. And since this is occur due to 1 unit force, and if A sub y apply to it, the deflection going to be this one. So now we are consider the deformation of these frames, this frame, and then we have, this is what? This is going to be the deformation, the displacement at A in vertical direction. This is also okay, and this is also. So what we have is, this is going to be 0 and equal to if downward is positive, delta A vertical, and downward is positive is minus F sub AA and then A sub Y. So what we have next is the A sub Y equal to delta, let's say, sub A divided by F sub AA. Okay, this is going to be the compatibility equation at A of this frame. So what next? Based upon this, the redundant can be determined by finding the displacement here, okay, and also the displacement here. That means over here and this one, and then we will use the method of virtual work to determine it, because it's one of the most convenient one. Or if you prefer, you may use the Castiglione theorem to determine it. So the third, just use the third, we determine the force and displacement relationship, okay, which is going to be delta sub AV and F sub AA, and then by using the method of virtual work, the method of virtual work, okay, and based on the method of virtual work, you're going to determine the deflection of this, right? So we have what's so-called the equation of virtual work. So the equation of virtual work, and then it says what? If you like to determine this, the delta, okay, sub AV, you got to what? You got to consider this frame under the application of the force, okay, and then what? You got to put the unit force into this frame in the same direction here. So let's say you got to put 1 point over here. This is 10 kilonewton. This is 2 kilonewton per meter. This deformation here, right? This deformation here is the delta sub AV. This is going to be the delta A vertical. And this one delta A vertical time 1 unit force. And what we have here is external virtual work, okay, and this external virtual work going to equal to the internal virtual work, okay, where the internal virtual work come from, okay, this one unit going to produce the moment, and this moment gonna time something to produce the work, so it's gonna time d theta. And everybody know that from the d square v by dx square equal to m over ei, and you have this one d by dx of what? Of dv by dx, and then this is also m over ei, and you also need have this one for d theta, that is going to be m over ei, and this one dx. If you put this is going to be equal to m and then d theta. That is going to be the internal virtual work, and you do the integration. And since the d theta is here, so it's going to be the integration of m, and then you have m over ei and dx. That is the review of the basis of the virtual work method. Now, what you need to determine is what? The M. The M is what? The M come from here because the M produce the rotation here. So the problem is come to determine the deflection. And next, what we do is we're going to set the coordinate. Okay, so now we set the coordinate. Let's set this is a kind of cantilever frame, right? So we set this one as the x1. Okay, this one from A until B, and also we set this one B until C. This is going to be x2. This is going to determine the M, right? This is going to be determine the M. And then what we have is you can cut this one. Okay, to determine the moment equation. So what actually we need to set, we got to find, okay, 4. We got to determine the equation of M and small m. Okay, and then basis on this we do two things. One, we set up the coordinate x1 and x2, and we will use x1 and x2 both determine the big M and small m. And then we also set up the direction of big M and small m. It's going to be the same. If you put this, it's going to have the first portion of this. This is 10 kilonewton, and you have this one for 2 kilonewton per meter, and this is going to for the capital M1. Okay, this is going to be M1. And if you cut this over here, your frame gonna be 3 centimeter, and then putting down a little bit here. And what we have is this is x1, and this is gonna be x2 subjected to the given force 10 kilonewton and 2 kilonewton per meter. Okay, and you set up the direction of this. That is going to be M2. Okay, this is going to be M2. This is going to be M2, if you like. And to determine this, you may do the calculation, summation of the moment over here. If you set this equal to 0, and this is going to be positive. So what you have is M1, rotate here, and the 10 plus 10 times x1 plus 10 x1, rotate in the same direction, and you get this. This is going to be 2 times x1 and in the same direction, so plus 2 times x1 and times x1 divided by 2, and this is going to be 0. So by doing this, just cut this one, you move this one, that is going to be equal to minus 10x1, and this one is going to be minus x1 square. Okay, that is the first equation for this M1. But for this M2, so again, summation of the moment equal to 0. Now, our M2 is here. M2 is going to take here. What we have is this one going to have this kind of moment arm of 3 meter, and it's going to be the same direction. So plus 10 times 3, 10 times 3. And then what we have is this one is going to be 2 times 3. And over here from here to here is going to be 1.5. So you plus this one of 2 times 3. Of 2 times 3. 2 times 3 is going to be 6. Okay, and times 1.5. And this is going to be equal to 0. And you may have this one, M2 is going to be, this one is 30 minus 30. And this one going to be minus 9. So your M2 is going to be equal to minus 39 kilonewton meter. Okay, this is another one that you can have for this one. Now, if you prefer, you may set this one. Okay, and this one is up to you. This one you may use up downward because you know clearly this is the downward. Okay, if you put the M1 in this direction, you may get the delta at A is positive. However, if you use this one by setting up A sub y equal to 1, A sub y equal to 1, this one going to be give you the negative. However, you may determine the F sub AA again by using this picture. So it's up to you to determine this. If you like, you may just project this one as you wish before. Just put this one, and let's have the point load here. Let's put it in black of 1.0, and this one gonna be the x1. And when do this, just keep in mind your deflection gonna be just opposite to this. It's going to be negative. It's okay for the convenience of this. So this one gonna be what? This one gonna be M1, small m1. And if you do the summation of the moment here equal to 0, you can see this one going to be really easily to determine of what M1 is going to be x1 equal to x1. Okay, and also for this, just cut it here. It's going to follow the same coordinate. So your frame gonna be cut here, and then you get this as the, just follow this, M2, small m2. Okay, and then this is going to be the same 1.0, and this is going to be 3 meter. And you can see that if you summation of the moment equal to 0, take the moment here, this one and this one is going to be opposite. So this one just get 3. Okay, you are ready now to determine the delta A phi. Okay, so this one just substitute into this delta at A vertical equal to what? Equal to integration of this one and this one. Just the integration from where? From this to this, from 0 to 3. Then you get this for minus 10 x1 minus x1 square, and then times this one is the x1, and then you dx1 by ei. That is the first portion of this, and then you plus, okay, for for the second one, for this one, you integrate it from this to this, integration from 0 to 3, and then you get this for minus 39, and then times this by 3, and then you have dx2 by ei. So that is the integration for you to determine the delta sub AV, and if you do it correctly, you may get this for 461. This is minus, okay, and this is minus. You will get this for the minus 461.25 over EI. This negative because the direction that you use is opposite to what it should be. Okay, so if you like to answer it clearer, just put this one equal to 461.25 over EI, and direction just opposite to this is going to be downward. So keep this in mind, and we will use this later. Next, now we have this already. Next, F sub AA. Okay, the equation of virtual work going to be 1.0. 1.0. 1.0 is what? 1.0 is the force. Let's X on this frame. Okay, if you put this one in this direction, that is going to be 1.0. 1.0 going to times F sub AA. Okay, we set A sub Y equal to 1. And then that is external virtual work. And this one going to produce the M. This one going to produce small m. Okay, that is going to be small m. And since this one has the deformation this way and sets A sub Y equal to 1, so this m is going to be this m. So that is going to be m square integration. Okay, and then you have the dx over ei. That means you got to determine what? You got to determine the moment, okay, of this one, x1, and also the moment of this one. For what we have is the x2, and then we have this already, right? So we have f sub AA equal to the first one, integration from 0 to 3, so x1 square, and then dx1 over ei. And the other one is here, plus 0 to 3. This is going to be 3 square, and dx2 over ei. Okay, this is going to be 9 times 3, 27 for sure. This is going to be x power 3 divided by 3, and it's going to be 9. Okay, so 9 plus 27, this is going to be equal to 36 over ei, and this one is upward. Okay, now we can determine the delta sub AV and F sub AA, and the sixth step, we're going to find the A sub Y and the reactions of the frame. Okay, by doing this, your A sub Y is going to be equal to 461.25 over EI, and then it's going to divide by 36 over EI, and EI cut EI, you get the A sub Y, right, of what? 12.81 kilonewton. So this one going to be 12.81 kilonewton. That is going to be the reaction that we are looking for it. So this is the important answer. From this, now we can start to find the reaction. If you like to define the reaction, come back into this one Okay, you're going to determine the reaction for this. Just put this one is 3. Again, the reaction here, okay, 3. And you also have this one for 3. And your frame subjected to at a 10 kilonewton. And this one is 2 kilonewton per meter. And you have the reaction, let's say this one gonna be C sub X, and under the force here I forgot, this is gonna be 12.81 kilonewton. So this one is up, down, so we should has this C sub Y here, and also we should have the moment here of M sub C. Now, if you like to do so, you do the summation of X sub X equal to 0. And since it's nothing, so your C sub X gonna be 0. So C sub X is 0. And if you do the summation of F sub Y equal to 0, upward is positive. Your C sub Y is upward. Okay, this one is downward of 2 times 3. This one is 10. So this is going to be upward. Plus 12.81 minus 10 minus 6 equal to 0. If you put this into your equation, your C sub Y gonna be 16 minus 12.81. Okay, so C sub Y is gonna be 3.19 kilonewton. And the last one, summation of the moment at C equal to 0. Now you have your M sub C, right? Your M sub C gonna be in this direction, so you put this one as the positive, and then you got to move your M sub C a little bit this way. So your M sub C is what? Your M sub C is clockwise, so M sub C is clockwise. And this one also produce the clockwise direction. This one gonna have time 3, so plus 12.81 times 3. And 10 is opposite direction, minus 10 times 3. And this one has direction here, minus 6 times only this time 1.5. And then this is going to be equal to 0. Now you can do the computation and you will get M sub C of 0.57 kilonewton meter. Okay, that is the reaction of our frame. Now, next thing, we're going to draw the shear diagram and moment diagram of the frame. And the frame can have the beam AB and the column AC. So let me put this one here. 3 centimeter from this one A and this one B. And we also have the column. That is going to be B and C. And for this, the shear diagram and moment diagram supposed to be here. And also this one supposed to be in this direction. And what we have is the force, that is 10 kilonewton. And this is going to be 2 kilonewton per meter. And this one is going to be 12.81 kilonewton. and for this one, no forces. And we have this one for 3.19. And also we have the moment here of 0.57 kilonewton meter. Okay, we're going to determine the end moment and end shear here, and if you prefer, in this case you don't need to, because there is no applied force at this point, so you can transfer from the beam to the column directly. But I like to show you to make everything clear up, right? Okay, this one, doing this one gonna be the V sub B. It's supposed to be 10 and 6, so it's gonna be this one. And then if you do the summation of f sub y equal to 0, you may have this one for your V sub B. Your V sub B is up, right? It's up. So the V sub B is up plus 12.81. Actually, you don't need to, but it's okay. It's going to be the same thing. This one plus this one, 12.81, and you're going to be minus 10 minus 2 times 3, and then equal to 0. And then you will get your V sub B equal to 3.19 kilonewton. And this one going to be downward here, and it's going to be upward here, and it's going to be downward here. So this one is 3.19, this one also 3.19 kilonewton. Okay, and since this one is 0.57, you can see that this one also, if you take moment here, summation of the moment equal to 0 here, so you m sub b got equal to this one, 0.57 kilonewton meter. And if this one is 0.57, this one also, and this one also, and this one also 0.57 kilonewton meter. Okay, that is ready for you to draw the shear diagram. Set this one as the x meter, and this one for 3 kilonewton, and this one is 0, this one is 3 meter, and then you have this one 10, this one 12.81, so 12.81 is larger. Just push this one about 2.81 millimeter. So we set 1 millimeter equal to 1 kilonewton, and then you got this one plus 2.81, and this one is 2. Okay, so your dv by dx equal to slope equal to minus 2. Okay, and you also know that this is going to be 3.19 up. Actually, it's going to be something like this, and this is going to be minus 3.19, if you know that. If not, you can prove it. Okay, you may prove this one by what? By V sub B minus V sub A minus 2.81, and it's going to be equal to minus of the area here, that is equal to minus of 2 times 3. So your V sub B is going to be minus 6 plus 2.81. So the answer is going to be equal to minus 3.19 kilonewton. Okay, you may prove this, and then your curve is going to be something like this, and it's close here, and this one going to have 0 kilonewton shear. Okay, and you should put this one for markup of the slope. And if you like, next we do the moment diagram. This one again, x meter, and this one is the roller, has no external moment, so this one is 0. And then we set this is moment kilonewton meter. Okay, this is start by 0 kilonewton meter, and then when you come here, you're going to have the slope here, and it's going to be dm by dx equal to 2.81, and then the slope gonna be changed. The dm by dx gonna be 0 here, and what is this? By the similar triangle, 2.81 divided by x equal to 2. So your x is going to be 2.81 divided by 2, and your x is going to be 1.405. So this is 1.405 meter. Now, you don't know the moment here, right? Yes, you know that. So the moment here, the moment here, minus here, minus 0 is going to be equal to the area here, 1/2 of 1.405 and times this 2.81. Okay, and then you will have the moment of this 1.974 kilonewton meter. Okay. Okay, and then you may set like a 2 centimeter. You have only 1 centimeter, so this is going to be 2 kilonewton meter per 10 millimeter, something like that. Okay, that is about very close to. Okay, this is going to be the dm by dx equal to 0, and then you point this one out here, very clear, and the curve gonna be something like this. And if you like, just highlight this, and then highlight this. Okay, and then what we have is the shear is going to be reduced, and until here, the shear is minus 3.19. So this one dm by dx gonna be minus 3.19. Okay, and the moment here is what? Is going to be this. You may check this one, moment, and this one going to same direction. This one plus 0.57 equal to 0. So it's going to be minus 0.57. Then the curve gonna be down, back, and here. Okay, and what we have is this one is the point of 0 moment, and it's going to be the inflection point, right? It's going to be the inflection point. And you may prove, if you don't know this, we may say m sub b here, minus here, minus 1.974, and then it's going to equal to the area here. And since this one is 1.405, this one is 3 minus 1.405 is going to be 1.595 meter. Minus 1.595, and then sorry, this is 1/2 of this, and minus 3.19, minus 3.19. Okay, you may have this one is negative and this one is positive, and you may have, if you do the computation, m sub b equal to minus 2.544 minus 2.544 and then plus 1.974, and this one is going to be minus 0.57 kilonewton meter. Okay, you may clear up this like here. Next, we do the shear diagram, moment diagram of the column, and again you may start by putting this one. And do we have shear here? We have no shear here, and this is x and then meter, and then you put this one of the 3 kilonewton, and since there is no shear, so this is gonna be 0, and the dv by dx w equal to 0, and all are 0. Okay, and for the moment, again this one gonna be x meter, and this one is gonna be m kilonewton meter, and what we have is this one sign convention of m, and this one in opposite, so our moment is going to be positive. Sure, since this one is the clockwise moment, so it's going to be 3.19. No, it's going to be up plus 3.19, and since the shear is 0, so dm by dx is 0, it's going to be constant, and it's close here with 0.57. Okay, that is going to be the moment diagram of this. And if you like, you may also draw the N diagram. Okay, the normal force diagram. And this is what? The compression. So you may set this one as the N kilonewton. And since it's compression, oh, sorry, this is wrong. This is going to be what? 0.57. And this is close by 0.57. And this one is compression, minus 3.19. And it's also, you can cut it anyway. It's going to be minus 3.19 until here, close. This is x meter. This is minus 3.19. This is called the normal force diagram. This one is the M diagram. And this one is the shear diagram, if you like. Okay, that is all for what we have. The shear diagram and moment diagram of the beam, and this one is shear diagram and moment diagram of the column. And then for the elastic curve, draw the shear and moment diagram of the frame. Okay, and then 6, we will draw the elastic curve. Okay, next we will draw the elastic curve. What we have is we have the frame of 3 meter here and 3 meter here, and this is fixed, this is the roller, and then based on the support we have, okay, as we mentioned before, the delta sub ch equal to delta sub cv, and this is going to be zeta sub c, all of them equal to 0, no movement. Under application of this one, the frame may move here, and what we have is this is going to be positive, and it's going to curve like this. And this was negative. Okay, it's going to curve like this. So this one may have the curve like this, and it's going to return back. Okay, this is going to be returned back like this, and it's going to keep the light angle here. Okay, and this one, you may see this is negative, right? This is negative, so this one going to curve like this for negative moment. And then what we have is this one going to curve and have the compatibility, no, and have the boundary condition here. And this is going to be the point of, this is going to be A palm, from A to A palm, and from B to B palm. And what else is going to be the same as before? And this is going to be what? This is going to be the inflection point. That is the point that moment change from plus to minus or minus to plus. And when you put the reinforcement, the reinforcement is going to change at this point also. Okay, and what else? This is going to be what we have mentioned, delta AH, and this is delta BH, and they are going to be equal. Okay, next. We put the reinforcement into this. Okay, and as I mentioned before, the reinforcement may be for the main reinforcement. With this one like this. Okay, and what we have is for this one, we're gonna put more reinforcement up into the inflection point. And again, for this one, we put it on the top, up for the negative moment on the top. And since this one is going to have the tension. So this is going to kind of extra reinforcement. So this is going to be the reinforcement pattern. Okay, this one going to be the elastic curve. Okay, that's supposed to be all we have for this example. We go back to check what we have. We start this problem by considering this frame that's going to have the degree of indeterminacy of equal to 1 by checking the degree of indeterminacy for unknown reactions with respect to the number of equation of equilibrium. So we have 1 degree of indeterminacy. And since we have the consistent deformation method, in which this consistent deformation method is a kind of what's so-called force method. Force method of structural analysis. That means we're going to use force equal to the redundant. Okay, so typically anyone can be the redundant, but the one that isolate from the author, okay, is going to be selected. In this one, it's really convenient to select the A sub y as the redundant, and the problem set us like that. And then they ask us to determine the reaction. After we find the redundant, we can then later to determine the reaction. Okay, it's here. And when we select A sub y as redundant, the frame will change from statically indeterminate to statically determinate. So we can consider the deformation of the beam, of the frame, and then we set up the compatibility at A. Okay, A sub y as A. The deformation of this one is like this, of this one is like this, and this one is like this. And at the point of A is 0 here, is equal to the downward delta sub AB and minus F sub A sub Y. You got this equation is a compatibility condition. And if you can determine the force relationship of these two displacement, you can get the A sub Y. And we have two methods to analyze the frame. One is the method of virtual work. And another one is the Castiglione theorem. It's better to use the method of virtual work. And then you set up what? The equation of virtual work. Okay, you set up the equation of virtual work. And the external virtual work is equal to the internal virtual work. That means you're going to determine the delta sub AV. That means you're going to put 1 unit force at point what? Delta A at point A in the vertical direction. Okay, so this is going to produce the capital M, this is going to produce small m. For the capital M, you go here. Okay, and for the small m, you may use this one in the opposite direction of this. And you keep in mind that the deflection delta sub AV that you get will be negative because you set this 1 point unit load of A sub Y in opposite to this. So don't worry, just do the same. You use your basic from engine static or the basic from what you have from the previous knowledge. You can find the equation of the moment M, capital M, and the small m. By doing so, you do the integration, you get the delta sub AV. And again, for this one, the deflection is over here. So it's really convenient in this way to set both m equal because the A sub Y cannot use. You got to set A sub Y equal to 1. So this figure and this figure, they are the same. And then we are the same pool, then this equation will be m squared. And you have this. Finally, you got the A sub Y here. From A sub Y here, you put the A sub Y over here. And then you can determine the reaction. After you determine the reaction, now you can draw the shear diagram, moment diagram, draw elastic curve, putting the reinforcement as you use the moment diagram and the basis of this. Okay, that's all we have for this problem. You guys supposed to try to work on this by your own, and if you close everything and you work as you watch my video clips and you do very good calculation, that's really nice. That means you have some skill to solve this problem. We are going to study on the analysis of statically indeterminate steel rigid frames. This frame has the pin at A and also at B. So this structure gonna have two reactions at the A, that is going to be A sub Y, and also we're going to have A sub X, and also at the C you're going to have C sub Y, okay, and the C sub X. This frame going to have the unknown of 4, and this frame is one free body diagram with 3 equations of equilibrium. So this frame going to have the degree of indeterminacy of 1, and we're going to solve this by the method of consistent. And you may read from this, they're going to set the horizontal force at C as the redundant. So this C gonna set as the redundant of this structure. Okay, and then basis on this, let's set this one. They set the C sub x as the redundant, is the kind of redundant force, is the extra force. If you determine the C sub x, and then you can find the C sub y, A sub x, and A sub y later. And now we're going to set the second one. We're going to set what to? We're going to set the compatibility. Okay, at what? At C, because they said C. That's C. In x axis, C sub x. And now you're going to what? To separate this beam, and then we're going to refer to by using the principle of superposition. Okay, and then we can separate the frame into two cases. And now we're going to this one. If we set C sub y as redundant, this one going to be the family frame, and then we're going to plus this one by the one that subjected to what? When we change when we set the C sub x as the redundant, the pin here change to the roller here. Okay, and then under the application of primary frame subjected to the applying loading. Okay, that's going to deform in this way. Since this one change from the pin to the roller, due to we set this one as the redundant, so this frame will deform like this under the application of the given loading. And what they said this one gonna have the displacement at this point along this one. Let's call it, this one is point C, move to the C palm. So we set this one as delta C, and let's say delta C horizontal equal to 1.328. Okay, and again at A we still have this pin, and now this is going to be the rigid joint, and this is going to be the roller, and this one gonna pass. This one already subjected to the applied force. This is going to the frame. Okay, subjected to the redundant C sub x. Okay, so this one gonna subjected to the C sub x, and C sub x is the unknown, right? So the C sub x also gonna take this one, move to this position, and then what we have is the deformation of this one. If this one move like this one gonna move like this, and this structure gonna have this kind of shape, because this one gonna take the right angle, and then the frame may assume to deform like this. What happened is the deformation here cannot compute directly because C sub x is unknown. So if we set C sub x equal to 1, okay, we can determine the deformation of this one by the deformation at point C due to the applied force at C. Okay, this is x equal to 1. If the total of C sub x, so deformation over here gonna be equal to this. Now we set the compatibility at C in the x direction, and what we have is this one is what? Let's see, if we set this one is positive, the deformation here is 0. Okay, and then what you have is equal to the deformation at here is delta sub ch is in this direction, and also we going to plus this one with f sub cc and c sub x, and now we have this one for 1.328. So our c sub x is gonna equal to minus of 1.328 millimeter, and then divided by f sub cc. Yes, by f sub cc. This is going to be the compatibility condition at c in x direction. And if we consider this, what we are going to do is we're going to determine f sub cc. Okay, so the next step is step 3. We are going to determine this is so-called the force displacement relationships f sub cc. Okay, and by using what? By using is depend on what do you have. We have the unit load method or the method of virtual work, and we also have the Castiglione theorem, but most of the time we use the method of virtual work, of virtual work, or the nickname is the unit load method. And we can see now only this one, so we come to here. The method of virtual work said the external virtual work will equal to the internal virtual work. Okay, and I can like assign you to determine this delta sub ch if you like, whether it's going to be 1.328 or not. And I also going to remark you when you do the calculation of this frame has unequal fractional rigidity. So you do the equation, you must be very careful on this. So only this you going to determine this. What happened is, what is going to be this external virtual work? When you like to determine the external of virtual work of this structure, you're going to determine what the direction you like to determine the deformation. So you like to determine the deformation or displacement at c in the cx direction. So the 1.0 assumed force is going to be there, 1.0, and this 1.0 assumed force is going to determine, it's going to multiply the f sub cc. Okay, the force time the displacement is the work, and this is assumed, so it is virtual work since it occur external of the structure. So it said it external virtual work, and then it's going to equal to the internal virtual work. This 1.0 gonna produce the moment m. So the moment m due to the 1.0, the moment m gonna time the deformation that occur on this structure is the d theta, and you guys know that is d square v by dx square equal to m over ei, and this is going to be d of dv by dx. Okay, so this is going to be what? d theta by dx equal to m over ei, and d theta is m over ei dx. Now it's going to be m over ei dx, and the integration due to the uniform deformation of this frame, due to the continuous deformation of this frame. And now for this, this is going to provide you with the m. However, the c sub x is unknown. We set c sub x equal to 1. If this c sub x equal to 1, the force applied to point C gonna be the same. So the capital M gonna change to small m. And then this equation gonna be integration of what? Of m and dx over ei. Okay, so now our problem reduced to determine what? Determine the moment that occur in this frame subjected to the redundancy sub x of 1.2. And now let's set the coordinate. Okay, so you set this, you do two things. One, you're going to set the coordinate. For this one, you're going to set x1 and x2. That's two. And you also need to set the direction of the moment m. Actually it's capital M and small m, but this time we reduce to only small m. So what would you like to set for this one? You may set this one as the x1. This one is x1, and this one as the x2. Okay, so before we can determine the equation of the moment, we determine the moment equation of m. Okay, we do two setup of that. And now what should we do? We must determine the reaction occur here. So now, before we can do other, we need to move this one a little bit, and then we set up this frame is 4 meter and 3 meter. So this one is 4 meter and this one is 3 meter. This one gonna be point A, B and C. This one subjected to the force of 1.0. And now what we have is, if you take the moment here, you may see you will have what? The reaction here in this direction. Since 1.0 gonna rotate clockwise, so this C sub y gonna rotate counterclockwise. And you also gonna have this one. This one is to the right, so this one A sub x gonna be to the left, and this one is upward, so this one A sub y gonna be downward. And now just know that this one is 4 meter, this one 4 meter, and this one 3 meter. You may do the summation. Let's put this one, the summation of the moment about A equal to 0. If you do this one, so the C sub x gonna time this one 4, sorry, C sub y 4 C sub y, and this one is going to be equal to 1 half the moment arm of this, of 1 time what? This is time 3. So your C sub y gonna be 3 over 4. Your C sub y gonna be 0.75. So this is 0.75. Okay. And next, what you may have is the summation of x sub x equal to 0. So A sub x equal to 1.0. And you also have summation of f sub y equal to 0. Your A sub y gonna be downward, okay, as positive. So your A sub y is gonna be 0.75. Okay, so that's all the reaction for this. And now you're gonna cut this one for x1 and this one for x2. So do the cut of that. That's one gonna cut over here. Okay, for the x1. So we have this one 1.0. This is going to be 1.0. this is going to be 0.75, and this one up. We have this one for x1, and we also need to do another cut, this one, okay, and then you're gonna have this, okay, and the force here still the same, is going to be 1.0, and this is going to be 0.75, and do the cuts there of x2. Okay, this is going to be x2. Now you're going to set the direction of the moment m. What would you like to have? Let's set this one as the small m1. Okay, and may set this one for the small m2, and then you may use the summation of the moment over here equal to 0. So this one produce 0 moment, only one. This one gonna be 1 times x2, so we have 1, and then 10 times x1, this one. And for this one, you do it again for the summation of the moment equal to 0. Just take moment here. What we have is this one gonna rotate. This is plus, and this is also plus. And if you take this, you may see this one 0.7 gonna produce in the same direction at m2. This is gonna be x2. However, this one gonna take 3 meters and going to be in the opposite direction of m2. So this is gonna be 1 times this one. 1 times this is 3 meters, right? So 1 times 3. And this one gonna rotate in the same direction as m2. When you move, this one is 0.75, and this is gonna be x2. Okay, that is gonna be the equation of m2. Now you put back into this, you have the equation for f sub cc is gonna be equal to, so this one integration of what? Integration of this one square, and also the integration of this one square. So f sub cc is going to equal to integration. For this orange one, that means you're going to integrate to this column. So integrate from 0 to 3. Okay. And this one gonna be x1 times x1. You have the x1 square. And then it's going to be dx1 divided by, this is only ei. Okay, ei1. Okay, and this one, the next one, we go to plus integration. Now you integration of the beam from B to C for the length of 4 meters. So you integrate this from 0 to 4. Now you do the parenthesis. This is 3 minus 0.75 and x2, and this is going to be square, and then you're going to dx2 by what? This is 2ei1, so 2ei1. Okay, now this is going to be x square, and this is going to be, that's term m2 square. If you do the integration, you do it carefully, and you will get this one equal to, this term is going to be x1 by 3. Okay, x1 power 3 by 3 from 0 to 3. So this is going to be 3 power 3 by 3 is 27 by 3 is going to be 9 over ei. Okay, and you do this again. If you like, you may separate this by your integration. If you do it, you're going to get this one by plus this term, going to provide 6 over ei1. Okay, this is going to be ei1, and the total of them going to be equal to 15 over ei1. and the direction is gonna follow this 1.0 unit. So the direction is gonna be in this direction. Now, you come back here. Over here is millimeter divided by this. So you got to go back. The EI is 60,000 kilonewton per square meter. So this one is equal to 15 divided by 60. Okay, and then this is 10 minus 3. So 15 divided by 60 is what? 15 by 0.25, and then 10 minus 3 and meter. And you don't want to have it in meter, right? You're going to have it in millimeter. So this one going to be 0.25 millimeter, and it's going to provide the direction in this direction. Now, you just put it back in the next step. So the next step for we find the redundant. We find the redundant and reactions. Now we plug it back to here. The C sub x gonna equal to minus 1.328 millimeter, and then is divided by 0.250 millimeter. You get this one as the negative of 5.312. This is gonna be minus 5.312 kilonewton. What we have is our C sub x is not in this direction. Okay, it's going to be in this. Sorry, it's not going to be in this direction. The C sub x is going to be in the opposite direction of this. Okay, now this one, the C sub x, gonna equal to 5.312 kilonewton, and the direction is gonna be this one. Now we have this one, C sub x of 5.312 kilonewton, and now you can see, if you know this, you can determine what else, the reactions at different point. So now this is 4. Just put this one in 4. We're going to determine the reaction. 4 and 3. So this one is 4, and this one is going to be 3 centimeter. Do the scaling, okay? Just do everything with the proper scale, and do it nicely. So the force here gonna be 220. That is gonna be 20 kilonewton per meter. And now we have the applied force here. This is 5.312 kilonewton. And if you take the moment here again, you can see this one supposed to rotate this one. I believe our C sub y should be in this direction. This is going to be 4 meter. This is 3 meter. And also this is 5.312. So this one is the A sub x. Okay. And you also going to have this one for the A sub y. And now we do determine this. Let's start by do the summation of the moment about A, B, C. About A equal to 0. And you can see the C sub y gonna time this distance. You're going to have a C sub y, and then time 4 C sub y here. And it's going to be in this plus directions. And this one also time 3 meter. Okay, this one gonna be in the same direction as C sub y, plus 5.312, and then you time is by 3. Now you have this uniformly distributed load. Okay, and then it's going to rotate in the opposite direction, so it's equal to, this is gonna be 20 times 4. So this is 20 times 4. That is going to be 80 Okay, and then the AT is going to have the line of action here. So the distance here to here is going to be 2 meters. Now, you have the C sub y. If you do it carefully, C sub y is going to be 36.02. The C sub y is going to be 36.02 kilonewton. Okay, this is going to be 36.02 kilonewton. And now, if you do the summation of x sub x equal to 0, and this is positive, your A sub x is going to be equal to 5.312 kilonewton. Okay, this is 5.312 kilonewton. And the last one, summation of f sub y equal to 0. You put this one upward, positive. So your A sub y gonna be, A sub y is up, this one up, okay, plus 36.02, and that is gonna equal to up, this one is downward, equal to 80, and then you may have your A sub y equal to 43.98 kilonewton. Okay, that's all we have for the reaction. And now the 5 step, you will draw the shear diagram, moment diagram, okay, and elastic curve. Okay, that is going to be the next step. But before you can do that, we're going to separate the beam and the column. Okay, the column here is going to be 3 meters. And then you may project it to this direction to draw the shear diagram and the moment diagram. And also in this direction, you may have 4 meters, right? So this is going to be 4 meters. And then this is going to have the uniformly distributed load of 20 kilonewton per meter. This is 4 meters. This is 3 meters. Now, you may elapse this a little bit to provide the area for this. Okay, now what we have is the reaction. We have A sub x of 5.312 kilonewton and A sub y with 43.98 kilonewton. And this way you have this one of 36.02 kilonewton, and this one is 53.12 kilonewton. Okay, from these two segments of the frame, you may see which one you're going to determine the end shear and end moment here. Also, the end shear and the end moment here. Now, which part is going to be easier? I believe this one going to be easier than this one. Okay, because this have the uniformly distributed load. If you prefer, you may do this one easily. This is going to be 43.98 kilonewton, and this one will produce 5.312 kilonewton. And due to this is going to have the moment applied here. If you take the moment over here, you can see this one going to rotate in this direction. So the moment here going to be in this direction, and you may call this one as the M sub B. Okay, so the summation of the moment at this is A, this is B, at B equal to 0. This is M sub B. M sub B will equal to, this is 5.312, and time 3 meters. So your M sub B gonna be 15 point what 15.94 kilonewton meter. And if you prefer, you have the joint B here, and you may know that since the joint B have no applied force, you may transfer this one directly into this, or you may transfer this one into the joint first. It's up to you. This is going to be the moment. This is going to be the upward force. This is going to be the horizontal force. This horizontal force is 5.312, right? It's 5.312 is going to be this one, and this one going to be the 5.312 kilonewton. If you like, it can be transferred here to here directly if you like. This one down, this one up. Okay, so this one gonna be down, and this one gonna be up. Okay, this is gonna be 43.98 kilonewton. And the moment here applied to here is going to have the moment here, and also have the moment here of 15.94 kilonewton meter. Okay, you know this load and force, this force and moment transfer, right? When there is no applied force at B, you can transfer directly from the end B to this end B, and this is C. Now we're going to draw the moment diagram, and if you like, you may come this way for the column, and you may have this one for the X, this one X meter, this is 0, this is 3, and you may have this one for 3 kilonewton. Now what we have is, you move from the point of A here to the B, you get what, 0.53, that is 0.53, let's say 0.53 is about 5 millimeter. So this one is downward, minus 5.312 kilonewton, and W here is 0, so dV by dx equal to 0, so this is constant, and this is 5.312, just close this one. This one is minus 5.312 kilonewton, and if you prefer, just put this one for the slope. Okay, that is for the shear, that is negative. And for the moment, you have this one again. This one is X meter, and this one the A, since there is no external moment, this is going to be 0 kilonewton meter, and if you prefer, this is going to be M kilonewton meter. What we have is, the shear is minus 5.312, so the dm by dx is going to be minus 5.312. Okay, and you see, since one this is minus, so it's going to be minus, and over here is 15.94, and also if you do the sign convention of M, this M plus 15.94 equal to 0, so M is going to be minus 15.94. Okay, this is going to be about 1.5 centimeter. So we have this one for minus 15.94 on this. However, the slope going to be minus 0.312, minus 0.312, and minus 0.312 here. And then what we have is this moment going to cross this one. Clockwise is going to be positive. Okay. And now we move to this one. This one is negative, and this one going to be negative. Then this one is negative. It's going to deflect like this. And then we have for the beam BC, the beam BC. For the beam BC, we have for the shear. See here. This is up for 43.98. That's quite a lot, right? If you scaling, that's going to be a lot of shear force compared to this one. Let's do another scale. Another scale. Let's put this one 20 for 1 centimeter. That is still a lot. This is going to be 40. Okay, let's see. 40. This is going to be the shear kilonewton. And this one X meter. What we have is about 40 kilonewton for 10 millimeter. So this is a little bit larger than 10 millimeter. And we have this one 43.98 plus 43.98. And then W is 20, so the dV by dx going to be minus 20. And you know this is going to be 36. And this 36 going to close this one. This is going to be 36.02. So this is going to be minus 36.02. And if you don't believe this one will be sub C minus 43.98. And it's going to equal to the minus of this area. It's going to be minus 80. So V sub C going to be minus 80 plus 43.98. And your V sub C going to be minus 36.02. And your graph is going to be this one. And this is going to be 0. And you can determine X, right? This is 43.98 divided by X equal to 20. So your X is going to be 43.98 divided by 20. How much it is? It's going to be 2.2 meter. Okay. And then we can go further to draw the moment diagram of this one. Let's mark this one here for the moment. And this one is going to be the M kilonewton meter. And we have this one and this one. Okay, now what we have is this one, the rotation of the sine convention M plus 19.94 is 0. For this one going to be minus 15.94. Minus 15.94. So let's say it's maybe a scale about half of that, about 8 millimeter. We have 20 kilonewton meter equal to 10 millimeter. So the 15.94 about 8 millimeter. Okay, this is minus 15.94. And then you have 43.98. So the slope here, the dm by dx is going to be 43.98. Sorry, 98. And now the slope going to reduce until here. The slope is going to be 0. Okay. And the m here, we don't know yet. The m here, minus 15.94. And that's one gonna equal to this area. Okay, it's going to be equal to the area of here. When you draw the moment, you got to check the shear diagram. So that is going to be 1/2 of 2.2. And then 43.98 times 43.98. You do the calculation and then you may get your m equal to 34 point, oh sorry, m here minus of the minus, this one minus of the minus, this is minus, that's m here gonna be this one minus this one, 32.44 kilonewton meter. And then by doing this, this is going to be about 16 millimeter. This is 32.44 okay kilonewton meter, and dm by dx equal to 0, and your graph is going to be something like this. Okay, and then at this point is 0 kilonewton meter, you know that, right? And the slope here going to be what? The dm by dx is going to equal to minus 36.02. Okay, and then you have this one like this. You can check. This is going to be plus, going to be this one, and this one going to be minus. Now, your what? Your frame. You may draw it later here. 4 meter and 3 meter. So this one is 4 meter. 1, 2, 3, 4. And this one is 3 meter. And this is pin, and this is pin subjected to uniformly distributed load here and here, 20 kilonewton per meter, 20 kilonewton per meter. And you have this one is here, this is rigid joist, this is the point of inflection point. Okay, inflection point is about here, so this is going to be something like this. So this is concave upward, like this, and this is concave downward. Okay, and this is what? This is going to be taking care of the right angle, and this one going to rotate this way. So this is A, B, C, and what you may have is this one is going to be zeta sub B. This one going to be zeta sub A. And this one going to be zeta sub C, in which delta CH equal to delta CV equal to 0. And this one delta AH equal to delta AV equal to 0. And due to infinity small or no axial deformation of the column and beam. So we have what? Delta BH equal to delta B phi equal to 0. So we have only 3 slope left for you to determine if you like to find it. And later, if you do this, we may put 1, 2, 3, 4. If this is the reinforced concrete structure, again, we also can put the reinforcement into our frame. Okay, and you may see this one for the extra reinforcement. You may put this one to this one up into this is going to be the IP or inflection point. Okay, and it's going to be, let's say, this one. This is also the same thing, and this one going to put on the top. And since the moment here is like this, so the reinforcement here also be like this. So that's some kind of extra reinforcement that we may have, including with the typical reinforcement that we have for the column and the beam. Okay, that is for the elastic curve. and this is for the reinforcement. Okay, that is what we have for this problem. We can solve this one easier because this problem they provide what with some deformation. So our indeterminate frame, okay, when they select the C sub x as the redundance, the pin here change to the roller here. So under the application of the force that act on the primary frame, there is some deformation occur along the horizontal direction, and the set is for 1.38. Okay, and this frame will be plus this frame when it's subjected to the redundant force of C sub x. Okay, and since C sub x is unknown, usually we set C sub x equal to 1 and determine the deflection in this direction, and we call this F sub cc. And now if we like to determine the total of this, so we got to times F sub cc by C sub x, and then from this deformation you may set the compatibility condition or equation at c in x direction 0 equal to this one plus this one, and then you get the compatibility equation. When you find F sub cc, as you may determine this, okay, you can plug it back and then plug this one back, and then you get this redundant force. If this is in negative, so what they said due to this one will be incorrect. The direction reverse to this one. Now you can do the free body diagram, find the reaction. Also use the graphical method to draw the shear diagram and bending moment diagram, draw the elastic curve, put some reinforcement. Okay, you guys, you need to do some more practice by your own on this kind of problem, and I don't think this is hard. Okay, just require more practice. Today we have an example on the statically indeterminate rigid frames as shown below. This frame have two columns and one beam. This frame has the modulus of elasticity of 205 gigapascal. And if you may know, if you like to use the kilonewton, the 205 10 minus 9 Newton per square meter will change it to 205 10 power 6 kilonewton per square meter. And the beam has the moment of inertia of 2I, and the column has the moment of inertia of I1. So the beam gonna be 2 times moment of inertia with respect to the column, and this one supposed to be 67.510 minus 6 meter power 4, not this one. And they asked us to determine the reactions. We are going to have the reaction at the pin. Okay, so we supposed to have both d sub x and d sub y, and also at the A is a pin. Okay, we have one, and we have this one is the A sub x and the A sub y. So actually we have the total of four unknown reactions, and our structure gonna have one free body diagram with 3 equations of equilibrium. So this problem going to have the degree of indeterminacy of 1. So we're going to have one redundant force based on the consistent deformation. Okay, we need to have one redundant force. And the problem said they're going to provide that with the horizontal force, at D as the Linden force. So this one is going to be the Linden force. So based on this, what we have is we going to put the D sub y into this. And since we put D sub y into this, what happened is the support, when you put this, the support will change from pin at D to roller at D. So if you put this, the A is going to be the same. The A is going to be the same anyway. Okay, but the D will change to the roller. Okay, the D, and then what we have is under this frame will separate into two frame. So first one we separate the frames into two cases based on the principle of superposition. So this time we change this one into this one. Since you have d sub x, this support will change from the pin to the roller. Okay, and then what we have is the structure gonna have this deformation plus another one, but this one will subjected to the redundant force. So based on this, we got two frame. Is the primary frame that is subjected to the given loading. Okay, and another one is the frame subjected to the redundant force d sub x. Okay, is going to have two of this, and based on this deformation is going to deform under the application of the giving load of 2 kilonewton per meter. Okay, they're giving us the structure gonna have the deformation in this direction of 0.963. You may calculate this if you like to do so. This is 0.960. But for this one, let's put the d sub x into this direction. It's subjected to the d sub x. Okay, so this is going to move inward into this position, and what we have is the deformation in this direction, and usually we will set the d sub y into 1, and this is going to be f sub d, f at point d, due to the applied force at point d. So it's going to be f sub dd. And if you prefer, you may set this one will move this way, and to keep this as the right angle, this one gonna move something like this, and this is going to put in right angle and have the deformed shape like this. Okay, and second we will have the compatibility at D in the x direction. Okay, so you got to refer to basis upon the deformation of the frames. Okay, 3 of them. We may set the deformation in this direction is plus. So what we have is This one, even though it's changed from the pin to the roller, the d sub x gonna hold this, and basis upon previously know this is gonna have zero displacement in the x direction at d. And for this, you're going to get is for 0.960 millimeter in this direction, if this one is plus. And this one gonna be minus what? F sub dd and then d sub x. And now, your d sub x gonna equal to what? 0.963 millimeter and divided by f sub dd. Okay, that is going to be our compatibility equation, and based on this compatibility equation, after we determine f sub dd, we can find the redundant force of d sub x. So our next step, the third, we find the force displacement relationship. Okay, that is going to be f sub dd by using which method you prefer. You may prefer the method of virtual work, or if you read the textbook, the author textbook, you may use the classical theorem if you like. Okay, this one we use the method of virtual work. It have the nickname of unit load method. Okay, and if you basis on this, what you have is the virtual work equation. Okay, we have virtual work equation. The virtual work equation said the external virtual work is going to be equal to the internal virtual work. And what is going to be this one? The external virtual work, you got to have another frame this time. And what happened is your frame gonna subject it to a virtual force or the assumed force of 1 unit. Okay, so it's going to subject that to the 1 unit. At what point? The 1 unit is supposed to act at D. Okay, and in the same direction as the movement, this one in this direction. Okay, that is going to be 1.0. And again, you will have this one going to be f sub dd, right? Because we cannot compute it directly, we got to set the d sub x equal to 1. So this one is f sub dd, and the total of this is going to be f sub dd d sub x, as you have this, and that is going to have f sub dd. Okay, f sub dd, and then it's going to be equal to the internal virtual work. This 1 unit gonna produce the moment m inside this one, because it's going to bend. Okay, this frame like this is going to produce the moment, so this is produce moment m. If this one subjected to the d sub x, the moment supposed to be capital M, but this time you determine this, you set d sub x equal to 1, so this m, capital M, will change to the small m. So now the deformation here, as you may know, the d theta equal to m and then dx over ei. That is the change of the shape of this frame when d sub x equal to 1 due to the moments small m. So when you put this one going to be m square and then dx over ei. Okay, and then you do the integration because the deflection is the continuous function of this. Okay, now our problem reduced to what? To determine this moment m. After we determine this equation of m, we can determine the f sub dd. So we find the moment equation m. Okay, and before that, let's mean we're going to put this one. Let us put this frame into this area. Let's put this one for 4 meter. 4 meter is 2 centimeter. Okay, that is 4 meter is 2 centimeter. That is going to be 3 meter. That is going to be 1.5. Okay, and this is 2 meter. This is going to be just 1 meter. And this frame subjected to 1.0 force. So this frame subjected to 1.0 unit force. And again, if you put the moment here, you will see the force here going to be in which direction. The moment here gonna put this way. Okay, that is going to be counterclockwise. So the force here is going to be d sub y going to rotate clockwise to balance it. Now the force here going to be in this direction to balance with this. So this is going to be a sub x. And you also have this one. This is downward. So this one going to be upward of a sub y. So this one is 4 meter. This one 2 meter. This one 3 meter. And this is A, B, C, D. And then you do the summation of the moment at A first. At A equal to 0. This is going to have the counterclockwise direction. So this is plus. We have this one. Have the distance from here to here. It's going to be the moment arm of this. It's going to be 4d sub y. 4d sub y. And this one gonna rotate in the opposite direction, and the distance here gonna be 3 minus 2. So this is going to be equal to 1 and times this one of what? Of 1. And then you have the d sub y equal to 1 over 0.25. Okay, you may say it's going to be here of 0.25. And then it's going to be easier, just summation of x sub x equal to 0. So this a sub x is going to be 1.0. And if also you put this one in positive, summation of f sub y equal to 0. So this one you got to put upward is positive. Okay, so this a sub y going to be equal to d sub y of 0.25. Now we're going to set, to determine this, set what to think, set the coordinate. Okay, and then we have 3 of them. So we got to set, let's say this one is the x1. Okay, and this one is going to be the x2. And please set this one as the x3. Okay, Ajahn, can I set different from you? It's up to you. Okay, everybody have a chance to set. But if you set it, okay, you're going to do the same way as for different m's. Now you may cut this. Okay, for this and this one, and also for this one, for the free body diagram. So we have this one for the first portion of this, and this is going to be for the x1. Okay, this one from here to here, and then we have 1.0 and 0. This is going to be 1.0, and this is going to be 0.25. That is going to be the moment of small m1. Okay, and then we have further into this, and then it's cut here. That means it's going to move from here to here. And what we have is we're going to set this one for the x2. Okay, and what we also have, this one is going to be 3 meter. And again at the A we have this one for 1.0, and this one for 0.25. And now we are going to determine the M2 for this. And the last one, you got to project this one up here, and you have this portion of this one, and then this one subjected to the force of 1.0, and this one is downward 0.25. This is going to be 0.25, and this is going to be x3. Okay, you can do that easily, and then you put the m3 over here. This is going to be for the small m3. Now, if you like, you may see this one, summation of the moment equal to 0. Take the moment here. We didn't put shear and the axial force here because it's going to make things mess up. Okay, and the 0.25 have produced small moment. It cut this one, but this one going to produce the moment, and since it's moved in the same direction as m1, so this one gonna be 1 times x1. So 1 times x1, that means it's going to be in the negative, right? So it's going to be minus x1. It's going to be minus x1. To be minus x1 for this one. Okay, and then you may move further to this one. Just do take the moment here. Okay, summation of the moment equal to 0. Take the moment here. What we have is our m2 is in this direction, and what you have is the 1.0 gonna move in this direction. Okay, so you have m2 plus 1.0 gonna time this distance of 3. Okay, time 1. Okay, and then 0.02 gonna be in this direction and going to be in opposite, so it's going to be equal to 0.25, and then it's gonna time x2. It's gonna be equal to 0. Okay, so now this one is gonna be minus 3, and plus 0.25 x2. Okay, let me mark this one for the x1, marks this one for the m2, and the last one, if you do this one, you just to do the summation of the moment at this point equal to 0. So this one produce 0 moment, this one going to produce the opposite moments of m3, so this one gonna be time what? x3, right? So this one x3, and then you may put this one for this column. Okay, we have all the moment for this equation. Now we just put all of them into your equation. So this is going to be equal to, the first one is here, integration from what? From a to b, from 0 to 3, and this one is going to be minus x1 square, and then it's going to be dx1 over ei1. Okay, and then we move to plus the second one from b to c, integration from b to c from 0 to 4, and your equation is here is minus 3 plus 0.25 x2, and then it's going to be square, and now it's going to be dx2 divided by 2ei1. Okay, and the last one is here plus the integration. This time you integrate from here to here, from 0 to 2, and this one going to be x3 square, and then you do the integration of dx3 with respect to divided by ei1. Okay, and you got to do it carefully, and if you do it good, you're going to get this one for 24.333 divided by ei1. Okay, and then you come to this equation is in millimeter unit. So you got to do some calculation. This is going to be 24.333 and then divided by, if you go back here, this one and this one, okay, divided by 205 10 power 6, 205 10 power 6 kilonewton per square meter. And you also have 67.5 10 minus 6 meter power 4. Okay, and then you get this for 1.758, 1.758 and 10 minus 3 meter. And since it is positive, okay, that means it's going to be in the same direction of this. So F sub dd going to put from the right to the left. So it's going to be this one. And in the millimeter, it's going to be 1.758 millimeter. Okay, now we are ready to determine the redundant force. Okay, if you put this one and then coming to this 1, 2, and 1, 2, 3, and 4. Compute d sub x and determine the reaction of the frame. Okay, so this one gonna be easy. Our d sub x is here, so d sub x equal to this one, 0.963 is gonna be 0.963 millimeter, and then it's gonna divide it by 1.758, so divided by 1.758 millimeter. Okay, so our d sub x gonna be equal to 0.547 kilonewton. This is going to be equal to 0.547 kilonewton. And you can see, if you know this, the other reaction, we can determine it easily. Okay, now we arrive at this of d sub x, and we are going to determine the reaction. We go back again to this structure. Okay, we do the same thing. This one is 4 centimeter. Just put this one. Just put this one is 4 meter. Sorry, 4 meter. And this one is for 3 meter, and this one is for 2 meter. And the force that's act on this frame is going to be 2 kilonewton per meter, and we have this redundant of 0.547 kilonewton. And what we have is the reaction at this point d, that is going to be d sub y, and you also have this point of a. We are going to determine the a sub x, and also we are going to determine the a sub y. Okay, and it's very clear again, this is going to be 4 meter, 3 meter, and 2 meter. You do the same thing as before, summation of the moment at a, okay, at this a, equal to 0. Again, your d sub y gonna rotate counterclockwise, so this rotate counterclockwise is positive. The d sub y gonna time this 4 meters, so it's going to be 4 d sub y as before. Okay, and what we have, this one gonna rotate by this as before. This is 1 meter, and this guy gonna rotate in the same direction as d sub y, so you're gonna plus, okay, 1 and time 0.547, and then you have this. Okay, this is going to be 2 times 4, that is going to be 8 kilonewton and this is going to be 2 meter. Okay, and this is going to be rotate in opposite direction, so 8, and then it's gonna time 2. Now you plug everything into your calculator, you will get d sub y equal to 16 minus 0.547 and divided by 4. It's going to be 3.863 kilonewton. Okay, and then this is going to be our d sub y of 3.863 kilonewton. And then just do the summation of x sub x equal to 0. So this time is going to point plus. So our a sub x just in the opposite of this. So a sub x is going to be 0.547 kilonewton. Okay, and the last one, to do the summation of f sub y equal to 0. Now this one is upward. Okay, our a sub y, put this a sub y plus 3.863, and then it's going equal to 8. So our a sub y is going to be just 8 minus 3.863 is going to be 4.137 kilonewton. That is the reaction of this frame. Okay, 4 of them. This is a sub x equal to d sub x, and this is d sub y. This is a sub y, and now we are ready to draw the shear diagram and the moment diagram of this frame. Okay, so we got to separate each segment of this frame, and we will find the end shear and the end moment, and later on we will find the shear diagram and moment diagram. Let's see, this is 3 meter. Let's plug this one into this size and set this one is 3 meter. Is going to be a b and 3 meter, and you're going to put this one for 4 meter. That is going to be 4 meter BC, and this guy gonna subject that to the uniformly distributed load of 2 kilonewton per meter. This is 2 kilonewton per meter. This is gonna be C. And the last one that we have is the 2 meter column CD. Okay, this is gonna be DC, and what we have is the area that we will use to draw the shear diagram moment diagram of each segment, and after that you may need to combine them together. Okay, and what we have is 0.547. This is 0.547 kilonewton. 4.137. This 4.137 kilonewton. And this one 0.547. Again, this is 0.547 kilonewton. And this one is 3.863. Okay, this is 3.863 kilonewton, and then it's time to determine the end shear and end moment, and it's going to be very easy if you determine this. And this one upward, this one is downward. 4.137 kilonewton. You don't need to use the equation of equilibrium. If you prefer, you can do so, but if you use this, it's going to kind of mess up thing here, so I just neglect it. And this one is on the left to the right. This one is from the right to the left of 0.547 kilonewton. And then it also has the moment for sure if you take the moment here. Okay, you can see this guy will produce the moment in this direction. So this one gonna produce the moment in this direction, two balances. So if you do the summation of the moment at B equal to 0 in this direction, so our moment here gonna equal to 0.547, 0.547 times 3, and that is going to be 1.641. This is going to be equal to 1.641 kilonewton meter. Okay, and now this is joint B. You may prefer, if you like, to transfer the forces and no moment passing this joint, but most of the time you don't need to if this joint have no force and no moment externally applied to it. Okay, so if you know that this is going to be this way, and you may do it. You can do it as your homework if you like. We may translate it like this. This is going to be 0.547 kilonewton. This is down, so this is going to be up 4.137 kilonewton. And this moment gonna apply here. Okay, and if you like, you may put this one 1.641 kilonewton meter. Okay, that is for the point B. Now again here 3.863 to be downward here, and then it's going to be upward here, and this is 3.863 kilonewton. 0.547. Okay, this is also 0.547 kilonewton, and it's going to be here. Okay, 0.547 kilonewton. At the moment, okay, this one going to have 2 meter, and this is going to rotate in this direction. So there is going to be the moment here, and the moment here we call it M sub C, summation of the moment, C equal to 0. Just take moment here. So 0.547 times 2, 0.547 times 2. And if you like, you put it into your calculator, and then you get this one for 1.094 kilonewton meter. Okay, that is the end shear, end moment, and end axial force for each member. Now, if you prefer to draw this, you should start from the column, and also you may do the zooming on this. Okay, for this one, let me put this one. This is going to be the column, and then this is downward. So we have this X meter, and this one gonna be the shear kilonewton, and this one is 0 meter. This is 3 meter. Now this one is downward for 0.547. Let's see, 0.547. What the scale is supposed to be, if you like. Well, let's say 5 millimeter per 1 kilonewton. Okay, if you like. This is going to be 0.5, right? And let's see, this is just very small, and then this is going to be 4 point something. That's a lot. So just put this one only 2 millimeter. 2 millimeter for 0.5 kilonewton. So 4 millimeter for 1 kilonewton. So this is going to be about 2 millimeter, and then this is minus 0.547 kilonewton. Since W is 0, so the slope here gonna be 0, and you will get this in parallel like this. And this is going to be minus 0.547 kilonewton, and this is put 0.547 up to close this, so this is negative here. Okay, and then we come to the moment diagram of this. Let's put this one is going to be negative because the dm by dx gonna be minus moment kilonewton meter, and this is gonna be 0 kilonewton meter because no moment apply here. And what we have is gonna be dm by dx gonna be equal to v minus 0.547. It's gonna be something like this. And then it's going to be equal to minus 0.547 all the time. And the moment up here is what? If you put this one, so m plus 1.641 equal to 0. So this is going to be minus 1.641. Okay, that is going to be 1.641 times 4 millimeter. That is going to be about this. Then you have this. This is going to be minus 1.641. You don't need to put them in kilonewton because kilonewton is here already. Okay, and then this one going to close, and this one is going to be negative. Since this one is negative, so the deformation going to be concave like this, downward. Okay, that is for the column, right? So we move for the beam. For beam here, and for the beam, what we have is this one 4.137. If you use scale this, that is going to be a lot, a lot. And then the shear here going to be very large. It's going to be about 4 times 4 is 1.6 millimeter. That is going to be a lot here. Use to scale that, it's going to be about this. Okay, this is past 4.147, and if you prefer, the scale is no good. So this is V kilonewton. And again, this is 3.863. The duty is this is going to push this one like this with 3.863, and you may see this is going to be minus 3.863 to push this one to the 0 here. Okay, so this is x meter and this is v. So we have up here, and then the dv by dx going to be minus 2. And then you will have the graph like this. This is 4 meter. You got this from 0. Okay, that is going to be the shear diagram. And what we have is, what the distance here is, what, 4.137 divided by x equal to 2. So this x equal to 4.137 divided by 2. And it's going to be 2.0685 meter. Okay, that is for this shear is plus, this shear is minus. And then we have the moment. Okay, moment again. And this is going to be the m kilonewton meter. And what we have is the direction of conventional m here. And what we have is what? This is going to the same direction. So this is 1.641 is going to be negative. Okay, this is going to be negative. Minus 1.641. Written here already. No way, it's that one. And then we have the dm by dx. Dm by dx equal to v 4.137. So this one is up. And this one we have the shear here is 0, so the dm by dx equal to 0. And what is the moment here? We don't know yet. The m here, minus of minus 1.641, and then this one minus this one equal to the area here. Equal to 1/2 of 2.0685 and 4.137. And if you put them into your calculator, m here is going to be 2.637 kilonewton meter. Okay, so this is 8 centimeter, 8 millimeter for 1.6. This is 1.3. And if you prefer, you may put this one, something like this, and this value gonna be up here. Okay, to make this thing go together. Now, about this, the moment, conventional moment here is this, and it's got the same direction as 1.094. So 1.094 is going to be negative, about 5 millimeter. This is going to be minus 1.094. And we're supposed to have this one, dm by dx equal to minus 3.863. And our curve gonna be something like this. Okay, and this is plus concave upwards. This is minus concave downward, like this. Okay, and we have the last one for the column here. And again, this shear is upward. Let's say this is x meter. This is 0.547 upward, 2 millimeter, 0.547. This is V kilonewton. And then W is 0, so the dV by dx equal to 0. And then this one downward closes. Okay, and the last one, we have the positive slope. So okay, the moment here is 0 kilonewton meter, no moment, and dm by dx equal to plus 0.547. Okay, and you can see this moment and this moment is in opposite, so it's plus, so it's up here of what, of this one. And then this is going to be your graph. Okay, and if you prefer, you set this one, just put this one to indicate your slope, and this one, okay, also this one and this one to indicate your slope. And now for this, just put this one for the slope here, this one for the slope here, this one for the slope here. And for this side, this is for 0. And this is also for the slope. Okay, that's all we have for the shear diagram and moment diagram of this frame. And now you are ready to use this to draw the elastic curve. Okay, if you prefer to draw the elastic curve, let's put this on the bottom of this. Just we have 4 meter. Okay, 4 centimeter we have 3 for the column. We have 2. This is A, B, C, and D. Subjected to vertical unit load of 2 kilonewton per meter. Okay, since this is I1, this is I1 also, and this is taller. Okay, so you can bend the taller column easier than you can bend the short column, right? So due to that, this guy will have the rotation like this, and this one supposed to have the side sway in this direction, and the B change to the B palm. And now this point, they're going to keep the right angle. Okay, and this is follow this. For this one, this is going to have this kind of deformation. So this may have this kind of deformation, and also it's going to keep this right angle. Now, what we have, this is concave downwards, concave upward. So this is going to concave, concave upward, and then it's going to concave downward like this, and concave downwards like this. And this is going to be the IP, the inflection point, okay, of this frame. And what do you have? This frame gonna say sway like this, and what we have, due to this no deformation, let's say due to very small, technically you may set it infinitely small deformation, small axial deformation of the columns and beams. So delta BH is equal to delta CH. Okay, this is going to be delta CH. They are equal. Also, delta BV is equal to 0. Delta CV also 0. So over here, we may have the slope, okay, of theta B, and over here we have the slope of theta C, and this is theta A, and this is gonna be theta D. So there are 4 slopes. Well, for slope to determine, if you like, and the delta AH equal to delta AV equal to 0 because it's pin. Delta DH equal to delta DV equal to 0 because they are pin. Okay, that is the elastic curve. Of this frame. I cannot go back to draw over there. No, over here is a better that a little bit more easier. And then what we have is reinforcement. Okay, we have the beam, the frame like this, the beam and the column. Now, what we have is this one. So for the positive, it's going to be like this. So this one going to have the reinforcement, the extra reinforcement like this. This one is negative. Okay, and this one has the reinforcement on the right, and this one we have the reinforcement on the left. Okay, that's supposed to be the reinforcement. If it is the RC frame, if it is the RC frame, if it is RC frame, this one is not, but if, okay, we do the practice. And you may know that usually we already have that. Okay, this extra reinforcement over there. Okay, it's depends on the detail of your reinforcement, but the main extra reinforcement for the corresponding to the bending moment is going to be like this. Okay, this is going to be the example that we have for the analysis of statically indeterminate rigid steel frame, and this frame have two columns and one beam, and the beam is different than the column. The problem gives us this deformation or displacement in the horizontal direction already. So the problem is easy, but it's better for you guys to go back and trying to determine this. And we also have this for the f sub dd. We can determine by typical the method of virtual work that we have. Okay, please do the practice to determine. Actually, this we call the delta dh. Okay, this is going to delta dh. And the also procedure after you determine the f sub dd, you get your redundant force, and you apply the redundant force. You determine the reaction. After you get all the reaction, you can draw the shear diagram, moment diagram. Okay, after that you can draft your elastic curve, putting the reinforcement if this frame is the RC frame. Okay, let's do the practice. Do a lot. You will get more skill and more skill after you do more practice. And hope you guys will enjoy what's learning here. And please practice, and you will get the ending sense and ending judgment after you pay a lot of attention to this. Okay, that is the end of the clips.